The primary functions of a battery management system are, first, to protect the human who is operating the battery-powered device, and that is our primary and ultimate concern. Under no circumstances should a human being ever be in danger from the battery pack. The BMS must be able to detect unsafe operating conditions and to respond to them in a way that warns the user and, if possible, eliminates the hazardous condition. A secondary concern for a battery management system is to protect the battery pack itself. We must ensure that the battery is maintained in a healthy operational window under all normal operating conditions, and we must also have fallback safety mechanisms in place in case of abuse of the battery system by the host application or other abnormal operating conditions leading to failure. Our algorithms must continuously monitor the state of health of the battery pack to be able to give guidance to the host application regarding the availability of energy and power such that the battery pack is never overstressed. That is, we desire to extend the life of the battery pack as much as possible, but we also, at the same time, desire to obtain as high level of performance as possible from the battery pack, so we do not wish to be overly conservative in our guidance or overly free either. We want to optimize a trade-off between performance and life. Part of this task often requires that we maintain the state of the battery within some prescribed performance window. That is, we may not be permitted to allow the state of charge to ever exceed some level, or on the other hand we may not be permitted ever to let the state of charge go below some level. So in computing power limits to inform the host application of the availability of power and energy in the battery pack, we must keep this kind of operational window in mind. As already mentioned, an important function of a battery management system is to provide information to the host controller regarding how best to use the battery pack, and this includes providing these energy limits and power limits estimates, but it often can also include telling a host controller what's the best way to charge the battery system right now, and in a vehicle, how much range might be available and many other possible things like that. Very simple battery-powered applications often do not require a sophisticated battery management system. For example, something like a flashlight simply uses its battery until all of the energy is expended, at which time you remove the battery and put in a new battery and throw the old battery into the recycle bin. Or if you are using a rechargeable battery like a nickel-cadmium battery, you would take that out of the flashlight and place it in the charger and charge it and then replace it into the flashlight. There is no need for a complicated battery management system to tell you when to do this. You simply recharge the battery when it's no longer fulfilling its requirement to provide energy to light the bulb in the flashlight. However, all lithium-ion battery packs need at least a minimal battery management system even in a simple application like a flashlight. And the reason is that lithium-ion battery cells are extremely efficient. While some other battery technology such as lead acid or nickel metal hydride can withstand some level of overcharging and still remain safe, lithium-ion battery cells cannot be safely overcharged. If a lithium-ion battery cell is overcharged, then at some point it will catch fire and explode. But even for lithium-ion battery systems, we don't necessarily require a complicated battery management system. In some cases, we might be able to get away with a very simple battery management system that merely ensures that the battery cell never has voltage exceeding some maximum level or that's below some minimum level, and this can be done with relatively inexpensive purpose-built electronics that integrated circuit manufacturers have designed for that exact purpose. So we might want to use a very simple battery management system for a low-complexity, low-cost application. Implementing a sophisticated battery management system requires a significant amount of processing, which means we need a fairly capable microcontroller to implement the algorithms. So there is a cost associated with sophisticated battery management algorithms. At the same time, it's important to understand that simple algorithms and inexpensive solutions will not usually be very good solutions. So there is an important range of applications for which we would like to implement more sophisticated battery management algorithms for better results. How do we make that choice? Here is a simple rule of thumb or a principle from years of experience that might be helpful to you. I propose that your entire battery system, including the battery management system, is considered cheap enough, inexpensive enough if when it comes time to replace it, you can no longer remember the last time that you replaced it. The idea is this. I cannot remember the last time I replaced the batteries in my television remote control, so I guess that means that the batteries for my television remote control were inexpensive enough for that application. If the batteries had been very expensive, I would have remembered for a very long time exactly when I replaced them most recently. So if you have a large battery, like for a grid storage application or for an electric vehicle, that battery will probably cost thousands of dollars or thousands of euro, and you know that if you had to replace this battery, you would remember for a very, very, very long time when you replaced it, how much you paid for it, and all of the details if you ever had to do so. So if your electric vehicle's battery pack failed, you probably would never buy that same model of vehicle again. So, battery packs and battery management systems for electric vehicles should last the entire life of the vehicle. Battery packs and battery management systems for other large-scale applications should last a decade or more without servicing. In order to maximize the life of a large battery pack, it's not possible to use simple algorithms and simple ad hoc methods. We really must use the best methods that we know about, and we must use the best battery cells that we know about, and the entire solution must be as good as we can make it. So a large battery packs represent a large investment, and so they motivate the best battery management electronics and the best battery management algorithms that we can afford. So this specialization will focus on teaching algorithms for managing large battery packs. Even so, the methods that you will learn also work for small battery packs, and it's simply a business decision, an economic decision, regarding when you use the robust but somewhat more complicated methods instead of using a less expensive but less accurate and simpler method. There are many applications of large lithium-ion battery packs. We have looked at some other applications also, but our main focus has been on automotive. So that means that many of the examples that I will share with you in this specialization come from our experience in this automotive domain. If the application that you have in mind is different from this, then you can still gain from this experience, but there will be some distinctions almost certainly in some of the smaller details in how you implement the algorithms. Now, automotive applications for large lithium-ion batteries are a really growing market right now. In 2001, there were no vehicles having lithium-ion battery packs. And in fact, there were only 2 hybrid vehicles in the United States, and both of these used nickel metal hydride battery systems. Both of those vehicles were hybrid electric vehicles. So, they had both a gasoline engine and an electric motor that is powered through the battery pack. The gasoline engine provides the average power demand required by the vehicle, and the electric motor and associated battery system handles the difference between the average and some peak power demand. And also, when the vehicle is coasting or braking, it can accept some power from the drivetrain to do some on-demand recharging of the battery as well. And the reason that this is helpful is because the gasoline engine operates most efficiently only in a small range of speed and torque. And if we can maintain the engine within that small range of speed and torque, then we can get good fuel economy. The battery and the motor provide the excess power or absorb the excess power, so that when the motor and the engine are combined, the power provided is able to meet the load demand required by the driver. The battery and motor operate efficiently over a much wider range of speed and torque than does a gasoline engine, so the overall efficiency of a hybrid electric vehicle can be much higher than an equivalent standard gasoline-powered vehicle. The battery pack for a hybrid electric vehicle can be relatively small, and the reason for this is that the battery pack is not required to provide an enormous amount of energy. It provides very little energy usually in the hybrid electric vehicle, and the vehicle is not able to drive any distance at all on the battery pack power alone. The battery pack for the hybrid vehicle simply provides the differences between the average and that peak power. So the photograph I show you on the slide is the well-known Toyota Prius hybrid electric vehicle, which started out with nickel metal hydride battery cells, but I believe that in some versions, they also are coming with lithium-ion battery cells at this point. Another hybridized vehicle is known as a plug-in hybrid electric vehicle. These vehicles have larger battery packs than a standard hybrid electric vehicle, and consequently they do have some all-electric range. That is, you can turn the gasoline engine off and drive simply with the motor that is powered by the battery system. Plug-in hybrid electric vehicles can get much better fuel economy than hybrid electric vehicles simply because they don't use gasoline as often. And plug-in hybrid electric vehicles usually operate in electric-only mode only at low speeds, and at high speeds we must turn on the gasoline engine in order to meet the demand. The plug-in hybrid electric vehicle in this photo is the Ford C-Max Energy, which has approximately 20 miles range or about 32 km range in all-electric mode without the gasoline engine running at all. There are a range of sizes for a plug-in hybrid electric vehicles. Some have a range of about 10 miles or 16 kilometers. Others have a range of more than 50 miles or 80 kilometers. The larger range versions sometimes operate in electric mode even at high speeds and are sometimes known as extended range electric vehicles. That is, we consider them to be electric vehicles almost all the time because they have full power capability and a fairly decent range capability. But the gasoline engine can turn on in order to extend the range of your electric vehicle just like it does in a hybrid. For most people, an extended range electric vehicle makes a lot of practical sense as their primary vehicle. If your daily commute is less than 50 miles or 80 kilometers, then you can plug your vehicle into the wall outlet at home and never require going to the gasoline station at all. On the rare occasions where you must drive more than 50 miles or 80 kilometers, there's still no problem because there's still the gasoline engine and it will turn on and drive you as far as you want to go. From a battery perspective, extended range electric vehicles are very similar to plug-in hybrid electric vehicles except they have larger battery packs to be able to store more energy for this longer range and also to be able to deliver more power so that we can operate in electric-only mode even under full load. And the extended range electric vehicle in the picture to the right is the Chevrolet Volt, which has an all-electric range of about 53 miles, or a little over 80 kilometers. So you can see that we are progressing from hybrid electric vehicle to plug-in hybrid electric vehicle to extended range electric vehicle, and in every step of the progression, the gasoline engine is used less and the electric power from the battery is used more. So the ultimate conclusion is a pure battery electric vehicle where we remove the gasoline engine entirely and leave a vehicle that's powered only by its battery and electric motor. And so, people call this an electric vehicle or sometimes a battery electric vehicle. These vehicles have the largest battery packs because they must rely exclusively on the battery energy for range and for power. The electric vehicle in the picture on the right is the Tesla Model S, and many of its configurations has over a 300-mile range. And remember I said in 2001, there are only 2 hybrid electric vehicle models in the United States, and neither were lithium-ion. Well, the founder of Bloomberg New Energy Finance, Michael Liebrecht, has said by 2020, there will be over 120 different models of electric vehicle across the spectrum. This isn't just hybrid electric vehicles or plug-ins, this is pure electric vehicles. These are vehicles that have already been announced by the manufacturers. It continues by saying, these are great cars. They will make internal combustion look old-fashioned. So, this market is seeing incredible growth, and there is a demand for engineers who can build battery management systems, and who can write battery management system algorithms. All of these vehicle applications we've looked at use battery packs that are large in some sense. Clearly, they are larger than the battery in your mobile phone. These applications also use batteries that are high voltage. For example, a laptop battery might be on the order of 15 volts, a cell phone battery might be on the order of 4 volts, but a vehicle battery is usually between 250 volts and maybe even 600 volts or higher. Vehicle applications also require high electrical current, often over 1,000 amperes under peak load, and this is very different from a portable electronics application where much less current is required. So even though there are some distinctions in design between the battery systems required for a hybrid electric vehicle versus a battery electric vehicle, the commonalities are more significant than the differences, so we are going to look at the distinctions in design only when we need to do so. But more often, we will look at fairly generic battery pack design with a fairly generic algorithm requirements that it can apply to any type of battery application. And so, when I talk about a vehicle application where we don't really need to make distinctions between what kind of battery-enabled vehicle we are talking about, I will simply refer to the whole class of electrified vehicles as XEV where X could be H for a hybrid or PH for plug-in hybrid or A for extended range and so forth. Of course, there are other large-scale applications. For example, there are emerging applications where the utility grid uses large batteries for different purposes. One is for storage. We can store excess generating capacity in a battery system for later use when the grid load exceeds generating capacity. Now batteries may not really be the best choice for grid-scale energy storage, something like pumped hydro might be a better large-scale solution, but there are still cases where grid storage does make sense such as for remote locations where microgeneration is done. Another example of a large-scale utility application is for grid backup. Suppose some maintenance must be done on a local power distribution station. Normally, Your entire neighborhood would be without power while the maintenance is being performed. But if a large mobile battery pack, perhaps on the trailer of a semi-truck, were to be connected to your neighborhood while the neighborhood is disconnected from the power station, then your neighborhood could receive power while the maintenance is being done and you would never even know that there was a power outage at all. Another great application is known as frequency regulation, which deals with relatively small amounts of excess generation capacity or excess load and buffers the grid against large power swings over a relatively short time scale of the order of minutes rather than hours or days, as the grid is often scheduled. So, all of these grid-type applications are being investigated by utility companies, even though not very many have been implemented at full scale at this point. But it appears
so far in this course, we spent almost all of our time looking at how battery cells operate, and during the first to fourth sections you learned how standard electrochemical battery cells work. And during the fifth and ninth sections you learned more about how lithium-ion battery cells work and how they work a little differently. Now we are beginning to turn our attention to the battery management system that controls and manages battery packs built from many lithium-ion battery cells. And during the next few sections, you're going to learn the principal requirements of a battery management system and some ideas of how those requirements can be satisfied. We will not discuss algorithms themselves in any depth. We will leave that for later in the specialization to do so. Again, at this point, our primary objective is to get a fundamental understanding of what a battery management system is and what it must do. Remember that a battery management system, or a BMS, is something that we called an embedded system in the first section of the course. An embedded system is made from purpose-built electronics combined with purpose-built software or processing in order to enable a specific application. The photograph here shows the battery management system electronics from a forward, C-max energy plug-in hybrid electric vehicle. When you disassemble the battery pack, you also disassembled the battery management system casing to see what was there, and this is what we found. You can see that this battery management system has a large number of electronic components on a circuit board, and around the edges of the board you can see connectors in a variety of different colors. Most of these connectors are wired directly to the terminals of the cells that enable measuring the individual cell voltages. Others of the connectors are wired to different other computing elements in the vehicle, such as the master vehicle controller and so forth, in order to enable the battery management system to communicate with the host application. What are the available limits of the battery pack? All of these connectors turn out to be slightly different mechanically from one another, so it's physically impossible to plug in the wrong connector in the wrong connection. And when we look at the circuit board itself, you can also notice that the color of the circuit board is different on one side from the other. The left side of the circuit board houses most of the analog sensing elements that measure voltages and perform balancing that we will discuss in the coming sections. And the right side of the circuit board contains most of the digital elements to do the computations required by the battery management system. When we are operating the battery pack and the battery management system, the cells in the battery pack are going to generate some heat, because of some resistance in them, and that heat must be dissipated by the thermal management system of the vehicle. But it also turns out that the electronics of the battery management system generates heat that must also be managed by the thermal management system of the vehicle. So this circuit board that you see here is housed in a metal case using thermally conductive paste so that there's good thermal conductivity, but bad electronic conductivity between the components on the circuit board and the metal casing, so that heat can be removed from the metal case. And in this picture I scraped off that paste so you could see the main circuit elements more clearly. The majority of the paste was over the elements in the top left part of the battery management system. It looks almost like a grid. And also over some of the computing elements to their right, where the computing elements may generate more heat, but on the left side, the grid-like elements are a lot of individual resistors that are used when balancing the battery pack using a passive balancing scheme, where excess energy in some cells is dissipated as heat through the resistors, and that heat must be removed through the thermal paste, through the casing of the battery management system using the thermal management system of the vehicle. The example battery management system on the previous video was from a vehicle application, but regardless of what the application happens to be, the battery management system has a few different priorities. The first priority is of course safety. A battery management system first and foremost is designed to protect the safety of the human operator of the host application. So the battery management system must detect unsafe operating conditions and respond to those in some way. In some applications, the battery management system is not given the authority to take action on its own. So in that case it must recommend certain actions to the host application that it can take instead to perhaps turn off the battery system and shut it down. The second priority of a battery management system is to protect the battery pack itself. This is especially important if the host application fails in some way and is beginning to cause abuse to the battery pack. In many cases, the battery pack has some authority to detect these conditions and to disconnect from the load if it is sensing some abuse that would cause damage to the battery pack, and especially if it's sensing some abuse that would cause a safety hazard instead. A third priority of a battery management system is to prolong the life of the battery as long as possible under normal operating conditions. And this is in a non-abuse situation when the host application is correctly following all the directives that the battery management system gives. We want to make sure that we give those directives in such a way that we maximize performance in some sense, but we also maximize the life, and we do this generally by informing the host application what is the maximum power that can be drawn from the battery pack or that can be sunk by the battery pack at any point in time over some time horizon. Another priority is to maintain the battery pack in a state in which the battery pack is able to fulfill all of its functional design requirements. In some applications like an automotive application, it may be a requirement that under every circumstance I retain enough reserve in my battery pack that I can always accomplish some acceleration event for a short period of time or some braking event for a short period of time. So in other words, I can give some amount of power or sink some amount of power for a safety reason. In that case, I must make sure that the state of charge of each of the cells does not get too high so that I can always accept some charge, or it doesn't get too low so that I can always deliver some charge to the load. So in those cases the battery management system will not give permission to the host application to discharge the battery pack beyond some point or charge beyond some point. And the final design priority is performance. For the battery management system, to inform the host application how to make the best use of the battery pack right now. And I might not be near any of the major limits of the battery pack where it might be close to overcharge or over discharge, but I might still want to know what is the best way to use the battery packs that I prolong the life and get the most performance possible. And we do this usually again by informing the host application what the power limits are right now and sometimes also how to charge the battery pack. What is the best profile of charging power versus time to charge this battery pack in a way that extends life, but charges quickly. In order to achieve these priorities, the battery management system must be connected to all of the internal battery pack components to be able to sense and understand what is happening inside of the battery pack, and it must also be connected to the host application to be able to communicate with that application, to give its recommendations on how the battery pack should be used. And the diagram on the right of this slide shows this in a block diagram kind of sense. The cells of the battery pack are shown as blue, and they are drawn as being connected in series with one another using thick lines to represent the high power primary high current connecting path of the battery. And these high power lines are connected to the host application load through devices called contactors, which we will study in more detail later on, but you can think of the contactor as being a switch, an on or off switch that either connects the high voltage, high power battery pack to the load or disconnects it from the load under software control. The same unit that controls the contactors often does all of the high current and high voltage monitoring of the battery pack. And we can also see that the battery management system must be connected to the individual cells in the sense that it must be able to measure all of the cell voltages and perhaps even all of the cell temperatures. The battery management system is further connected to the thermal management system, the cooling system usually inside the battery pack. And so everything that you see inside of the yellow rectangle in the diagram is typically contained inside the enclosure or the physical enclosure of the battery pack. Outside of this enclosure you can see the host application with which the battery management system must constantly be in communication in order to understand the requirements of the host application and in order to convey the limits of the battery pack at this point in time. So when we think about how to achieve these priorities, we can divide the functionality of the battery management system into a number of major categories, and I will outline 5 major categories. The first requirement that we'll look at has to do with sensing and high voltage control. The battery management system must be able to measure all of the voltages of every cell in the battery pack, and it must be able to measure the overall battery pack current and different temperatures inside the battery pack as well. In terms of control, I must be able to control the contactors that connect the battery pack to the load and disconnect it from the load. In order to do that, we have to be able to perform an operation called pre-charging that you will learn about as well. We must be able to detect when there is a ground fault or an isolation fault between the battery pack and some point that should not be electrically connected but might be under some extreme conditions. And the battery management system must also be able to control the thermal management system. The second aspect of functionality that we will look at has to do with protection. In this case, we're thinking primarily of how do we protect the battery pack itself, how do we protect the battery pack against over-discharge, and how do we protect it against overcharge, and how do we protect against excessive electrical current, and how about a short circuit or extreme temperatures. The third area functionality has to do with interface. And under this category, we think about some of the requirements of the host application and how those rely on information that are known inside the battery pack. So these might have to do with computing remaining range in an electric vehicle. And we certainly need to be able to communicate with the host application itself. And in many applications, it's also important to create within the battery pack some kind of a permanent record or a permanent log of different conditions and have maybe a separate interface for diagnostics purposes as well. The fourth basic area functionality has to do with performance management of the battery pack. And this is where we will spend almost all of our time in this specialization, learning how to accomplish the requirements of performance management. This has to do with being able to estimate the state of charge of the battery cells, and estimating power limits, and how much energy is available and how to do that balancing or the equalization of the cells in the battery pack. The fifth and final area of BMS functionality has to do with diagnostics. This has to do with detecting abuse of the battery pack by the host application. It has to do with determining the state of health of the battery cells under either normal or abuse conditions. And in some cases, it also has to do with estimating the present state of life and predicting from that perhaps how much future life we expect the battery pack to deliver before the battery pack must be replaced and recycled. Are required really in any battery management system. It turns out that some applications find these requirements more important than other applications. In some applications, maybe we don't even implement all of these features because we are determined that they are not critical. In most cases, the question regarding when to implement a feature or not and how much effort we put into implementing that feature very well or not, has to do with how expensive it is to do so. If there were no cost associated with implementing all of these features using the best technology available, then of course, we would do that. But there is a cost associated with each one of these features, and so, we must make a decision. Is this cost really necessary in this application? So I have a rule of thumb to propose to you. If you are not familiar with the term, a rule of thumb is a broadly applicable principle that is developed by experience. This is not something that we can derive with math. This is more experiential and a little bit more ad hoc. It's not always true, but it's true often enough that it can be a guiding principle unless we have some more detailed analysis that contradicts the rule of thumb. So the rule of thumb I propose in this case is the following: your battery is cheap enough, it is inexpensive enough, if you cannot remember the last time that you replaced it. So for example, for my television remote control, it's operated using disposable batteries. And a few times a year, these batteries wear out and I must recycle the old ones and replace the battery cells with new ones. And if these batteries were very expensive, then I would remember with perfect precision the date and time when I went to the store and purchased a new battery pack, because it would be just nagging at the back of my brain at how much I spent to replace the battery, and how I have used that money for something that was more important to me, and how upset I am that I had to replace the battery. But it turns out, I don't remember the last time I replaced the batteries in my TV remote control. And so, by this rule of thumb, then that must mean that the financial investment in these batteries was low enough that any kind of more advanced circuitry in my television remote control that would have cost more money, would not really have been worth it. So, the battery must have been cheap enough. But think about the battery in an electric vehicle. The battery in this electric vehicle will cost thousands of dollars or thousands of euros to replace. So that if I had to replace the battery pack in my electric vehicle, I would remember for a very long time the exact date that I replaced the battery and the exact amount that I paid to do so. And it may turn out that I would never purchase that vehicle again or anything like that vehicle because I was just so upset by it. What do we learn from this rule of thumb? We learn that inexpensive batteries don't need to last very long. But that large battery packs are expensive batteries need to last as long as physically possible. So large battery packs represent a greater investment by the consumer and they motivate better battery management even if it costs more to implement that better battery management. This specialization is really focused on large applications with large battery packs, for example, vehicle applications or maybe grid applications. And the methods that we discuss are very general and they also apply to consumer electronics, but you have to make the decision of when does the cost of implementing a sophisticated battery management system with sophisticated algorithms, when is the battery pack so expensive that I can justify this additional cost. And honestly, the cost isn't that much more than you would using a simpler approach, but there is some cost. And even for the consumer electronics, many mobile phones nowadays have non-user replaceable batteries in them. So, that means that, in order to replace the battery, you have to make an appointment with some store. And you must take your mobile phone to the store physically, and you must wait while they replace it, and so forth. So there's a big opportunity cost in terms of time and even in terms of money to do so. So even for a fairly small battery pack, you might want to implement the best battery management that you can in order to extend that battery pack's life as long as possible, to have the greatest consumer acceptance possible because that's what's going to drive future sales and reviews and so forth. So in this specialization, we'll spend the majority of our time investigating fairly sophisticated methods that work well in any scenario. This sophisticated methods may require maybe some more expensive sensors and maybe some more expensive processes than some less sophisticated methods. So you may not be able to justify the methods economically in every case. We will spend a little bit of time looking at less sophisticated methods and that will allow you to perhaps implement both of them in simulation or even in a prototype to see which one works best for you. Which is the best trade-off? And in the end, only you can make the design decision for your particular application as to which is the best method to use. That you're going to see that in most cases, inexpensive electronics and inexpensive processes only allow for a very poor battery management. And if you were to spend just a little bit more on electronics and a little bit more for a better processor, you can build a much better battery management system that can extend battery management system is an embedded system that protects the safety of the host application operator. It protects the battery from abuse, it prolongs the battery life, it maintains the battery in a functional state and informs the host application regarding how to make best use of the battery pack at this present point in time. In order to achieve these priorities, we can come up with a list of battery management system functional requirements and place these lists into different categories. And the categories that we will look at this week and next are the following 5. The first that we will look at for the remainder of this week has to do with battery management systems sensing and high voltage control. Next week, we begin by looking at protection, then we look at interface, then at performance management, and finally, at diagnostics. We noted that there are different levels of sophistication in how a battery management system works and not every battery management system will implement all of the features that we talk about. But our focus is going to be on advanced methods that might have a higher cost but give better results in most cases. And based on what you learn, you will be able to make informed design decisions in your own application as to which features you implement and how to do so. So that brings us to the end of this lesson. As we continue this week, again, we're going to be looking primarily at high voltage sensing and control. But before we do that, there will be one additional lesson where we'll talk about the design of the battery pack itself and how the cells are organized into a battery pack and what we can infer from that design into how to design a battery management system as well. So that brings us to the end of this lesson, where you've learned in the previous video topic, you learned the 5 major requirements of a battery management system. And before we continue by looking at how a battery management system will meet these 5 requirements, I'd like to spend a little bit of time talking about the principle of modular design for a battery pack and how that modular battery pack design also informs and suggests a modular design for the battery management system itself. Since we're looking primarily at battery packs and battery management systems for large applications, these will usually involve batteries from which there will be a high power demand. And we know that power is equal to voltage multiplied by current, so a high power battery must deliver either high voltage or high current, or both. When we think about how to meet a high power demand, the first thing we could think about is by maximizing the voltage of the battery pack. But we find out that chemistry of individual battery cells is going to limit the maximum voltage of one cell. For example, most lithium-ion battery cells operate in a voltage range between about 3 and 4 volts give or take. So if we require a battery pack of higher voltage, then we can accomplish that only by connecting many cells in series. And when we do so, the pack voltage is equal to the sum of the voltages of the cells connected in series. An approximate analysis would be to take the nominal voltage of one of these cells and multiply by the number of cells in series to get a nominal battery pack voltage by that. We might also consider trying to maximize the amount of current that we get from a battery pack. When we do, we find that how a particular cell is constructed places some limits on the amount of current that we can extract from that cell or put into that cell. But we also know that if we put cells in parallel, the battery pack current is divided between those parallel cells, and so that the overall pack current can be much higher even for a limited amount of cell current. And we can approximate the amount of current that we can get from a battery pack as the number of cells in parallel multiplied by the amount of current that we could extract from any particular cell. We might also be interested in thinking about the capacity of a battery pack in ampere hours. If all of these cells have equal capacity, then the capacity of the battery pack is equal to the number of cells connected in parallel multiplied by the capacity of any individual cell. And so, from this, we can compute a rough but a pretty good estimate, pretty good approximation of the total pack energy and total pack power. The pack energy is equal to the cell energy multiplied by the number of cells. The cell energy is approximately equal to the cell capacity multiplied by the cell nominal voltage. So if we have Ns cells connected in series and Np cells connected in parallel, the overall energy is Ns multiplied by Np, multiplied by cell capacity, multiplied by cell nominal voltage. The individual cell power is equal to the maximum cell current multiplied by the nominal cell voltage. So the pack power is equal then to the number of cells multiplying the cell power, or Ns multiplied by Np, multiplied by the maximum cell current, multiplied by the cell nominal voltage. At least to a first order approximation, and we'll learn more exact methods throughout this specialization. But from this approximate analysis, we can conclude that in order to meet certain energy or power requirements in a battery pack, the product of the number of cells in series and the number of cells in parallel must meet some criteria. But actually, that the individual values of Ns and Np are quite flexible. For example, we might find that the product, for some application, must be 12. In that case, Ns might be 12 and Np might be 1, or Ns might be 1 and Np might be 12, or one of them might be 3 and the other 4, or one of them might be 2 and the other 6. So, from an energy and power perspective, we have a lot of flexibility in how we choose the number of cells in series and how we choose the number of cells in parallel in order to meet these requirements. So how do we choose them? Well, the choice is usually made by economic factors and by safety factors. For safety, we usually want the overall battery pack voltage to be less than about 100 volts DC, and this factor turns out to be a little bit arbitrary. It's possible to have a safety hazard at lower voltages or still even to be relatively safe at higher voltage depending on the environmental conditions. So, there are different professional and standards associations that come up with slightly different answers as to what is a safe DC voltage. For example, the National Fire Protection Association, the NFPA, historically had a maximum voltage limit of 50 volts DC before considering the battery to be a safety hazard, and more recently, they have raised their value to 100 volts DC. Automotive manufacturers tend to be very conservative, and so they prefer to have voltages of less than 50 volts in any part of the battery pack that might be exposed. Furthermore, at this point in history, the power electronics required for operating at voltages larger than about 600 volts turn out to become quite expensive quite quickly. And for that reason, most applications require a voltage of less than 600 volts at least at this point in time. So using both of these considerations, we tend to have limits on the number of cells that we would like to stack in series in a battery pack. So let's think about it the other way. Maybe we want low voltage but we want high current, but there are some difficulties with this approach as well. The problem is that power losses through wiring and other components, but primarily wiring, are proportional to the square of current. That is, if the electrical current passes through wiring that has some resistance R and the current is I, then the power loss through that wiring is I squared times R. So the bigger current is the much faster I lose power, I waste power. So, for efficiency, we would either need to reduce the resistance of the wiring or we need to minimize the electrical current. In order to reduce resistance, we need to have far thicker wire and we have more strands in the wiring. And the thicker it is, the more copper is required, and copper is a relatively expensive element. So we really would prefer to use thin wire having somewhat higher resistance in order to save on cost. This fact tends to put design limits on the number of cells that we wire in parallel. So, as we often find in engineering, there's a design trade-off. We need to make a compromise between the number of cells in series and the number of cells in parallel. A very common solution is to build battery packs from smaller modules of cells. Each one of these modules has a DC voltage that's less than approximately 100 volts. In order to maintain safety of a particular module, if a technician is opening the module to do some diagnostics or repair, and then you take these modules with individual voltages less than 100 volts and you wire the modules in series to make a higher voltage battery pack. And this approach, overall, makes the number of cells in series relatively large and the number of cells in parallel relatively small. So there still remains a high voltage hazard when we consider the overall battery pack and not just the module. But this hazard can be managed by proper care when servicing the battery pack and by putting mechanical service disconnects into the design such that when the battery pack housing is opened, it automatically disconnects the modules from each other. And so that there is no voltage inside the battery pack larger than about 100 volts when the case is open. In my experience, this is the most common approach to building a battery pack for vehicle applications. Cells tend to be wired in series more than they're wired in parallel. But there are some reasons why we might consider wiring modules in parallel as well, and we'll talk about that shortly. When we're discussing either modules that are battery packs that are made from cells where some are in series and some are in parallel, there's a common way of talking about this. Consider the battery pack in the photograph on the right side of the slide. We see that this battery pack is made from 6 individual cells and that these cells are wired such that pairs of cells make a module and 3 modules are then connected in series. So, overall, the number of cells in parallel is 2 and the number of cells in series or number of modules in series is 3, and this particular battery pack would be called a 2P3S pack, 2 cells in parallel and 3 cells in series. As an actual example, I show some photographs of components of a battery pack from a Nissan Leaf electric vehicle. On the left photograph, you can see an individual battery cell and you can see that it's a pouch format cell. And to the right side of that same photograph, you can see a module that is built from that cell. And if you open up that module, you find that it contains 4 cells internally, 2 in series and 2 in parallel. So we would call this a 2S2P module. In the right photograph, you see a cutaway of the Nissan Leaf chassis overall. And you can see that the battery pack is mounted underneath the passenger compartment of the vehicle, and the overall battery pack is built from 48 of these modules that we saw in the left photograph. And, in this design, some of the modules are stacked vertically and some of them horizontally in this battery area. In addition to safety reasons, there are some other reasons why building a battery pack from smaller modules can make sense. One is that the smaller modules are easier to handle by humans or by robots who are assembling the battery. The individual modules can be tested before integrating them into the pack, and if one module turns out to have a failed component, then it's much less expensive to service that module than it would be to service an entire battery pack. Ideally, the overall battery pack design would be made from multiple instances of the same module design, and ideally the same module could be used in different battery packs for completely different applications, and the reason for this is then that your non-recurring engineering costs, your NRA, to design the battery module would be amortized over many products. The engineers need to design one module one time only and then can reuse that design for many different applications, and it's less expensive than needing to design new modules for every single new application. As we proceed through the specialization, we will consider how modular design of battery management systems is done to support a modular design of a battery pack. In particular, we will tend to focus on design extremes, but the methods that you will learn are general and apply to designs even in between these extremes. So suppose that I determine that I need 3 cells in parallel and a battery pack and 96 cells in series overall. I might consider then the design shown in this drawing that you see on the slide. In this drawing, we take 3 individual cells and we join them together in parallel to make a module, and that module we call a parallel cell module or PCM because its cells are connected in parallel. And then we take 96 of these PCMs and we connect them in series to make the overall battery pack. One advantage of this approach to a modular design is that we know that battery cells connected in parallel must maintain the same voltage just electrically physically because of Kirchhoff's voltage law. So we need to measure only 1 voltage per every 3 cells, which reduces the cost of my voltage sensing and some of the battery management algorithms as well. And for the same reason, the individual cells inside of one of these PCMs will self-equalize or self-balance because they must maintain the same voltage overall. And so for these reasons it's very common to find battery packs that comprise cells connected physically in parallel before they are connected in series. But we could also consider the opposite design extreme as shown in the second illustration. It has the same number of cells in the same overall general configuration, but they are wired differently. In this case, we take 96 cells and we connect them in series to make one module called a series cell module or SCM. And then we take 3 of the SCMs and connect them in parallel, but only at the high voltage terminals and not at the individual cell voltage terminals. There turned out to be some additional complexities to this second approach. We are required to measure the voltages of all cells, which is true in any case for lithium-ion battery management systems, but in this case I need to measure all 3 times 96 or 288 cell voltages because they could potentially all be different, whereas in the PCM approach we are guaranteed that each set of 3, each module of 3 cells had the same voltage by Kirchhoff's voltage law. Here in the second approach they could all be different, and so we must measure them all. Also in the SCM approach, the individual cells will tend not to balance each other automatically, and so there are some additional requirements for balancing circuitry. So those are 2 disadvantages of the SCM approach, but there is one very large advantage of the SCM approach in some applications. Suppose we want to make a very large electric vehicle, maybe an electric transit bus or maybe a large piece of heavy equipment like a bulldozer or something like that. If this vehicle must have a very long range in some use cases, but relatively short range in other use cases. And if I put a very large battery pack to satisfy the most difficult use case, then I've really over-designed for the simpler, lighter use case, and it would be nice to have battery packs of different sizes that I could put in a vehicle for the different use cases. But using the PCM approach that's really not a feasible thing to do. But if I build a modular battery pack out of SCMs, then that allows me to have the same overall battery bus voltage with different capacities depending on how many SCMs I install in the application. For relatively low range I might use one SCM and have a certain voltage. For a much higher demand applications, I might answer 2 or 3 or more SCMs and I have exactly the same overall bus voltage. I just am able to draw more current from it so I can drive bigger motors or bigger loads, and that means that the design of everything outside the battery pack is common and I just plug in a certain number of SCMs, however many I need. So there is no additional design for a low capacity application versus a high capacity application. It's simply a matter of how many of these modules the consumer decides to purchase and install, and that can be a huge advantage. From our perspective in this specialization, it's possible to design battery packs and battery management systems for either one of these design extremes, and in fact most battery packs are some combination, some compromise between these extremes. For example, we might build a battery pack from 18-cell 3p6 modules. The module and power energy are that approximately 18 times that of a single cell. Turns out to be not exactly that in practice, and we'll talk more about that later on. But if I do one of these modules with 3 cells in parallel and 6 cells in series and then connect 16 modules in series, I come up with the overall design requirements of the application and I meet safety limits of the overall module voltage and so forth. So a modular battery pack suggests using a hierarchical master-slave battery management system design as well, and we'll talk about that on this slide and in the following slides. For example, we might have some of the electronics that are dedicated most directly to managing individual cells that are located inside of the module of cells that they manage. This design approach minimizes the wiring and the connections and the wiring losses in the overall battery pack. We would call the electronics connected directly to the cells a slave BMS, and this slave BMS has all of the electronics for measuring voltages, for measuring temperatures, and for balancing the individual cells. There is commonly a single master unit for every battery pack, and the master unit does the supervisory control of everything overall. It's directly connected to this circuitry that manages and measures the overall battery pack current and opens and closes the contactors. The master unit communicates with all of the slaves, and it can do this using a daisy chain architecture like the one drawn in the illustration. And in that case, the master talks to the first slave, and the first slave talks to the second slave, and the second slave talks to the third slave, and that any response goes from one slave to the other and finally back to the master. So there is one single bus on which everything is connected in a daisy chain kind of way. Or the master can communicate with all the slave units using a star architecture, where the master is connected in kind of directly to every single slave, and there's different approaches as well. In order to reduce wiring, some kind of a bus architecture or a daisy chain architecture tends to be the most popular in my experience. In a master-slave design, the slave has certain responsibilities, and the photograph shows an example that is a demonstration board that linear technology has made in the past to allow designers to experiment with voltage measurement using their 68 or 4 part. And now it's marketed under analog devices now that analog and linear have merged. This is a good example of a slave design, and you can look this up on the internet by going to the website for the 6804 part and looking up this demonstration board. It also has schematics and sample code and things like that you can work with. Even though it's a good example, it actually implements some functionality that not every slave needs to implement in practice. And so, the features of this demo board could be made smaller in a physical design. One of the principal requirements of the slave board is to be able to measure the voltage of every cell in the module. And the connector on the top of the board in the photograph connects to the wiring harness that connects to each of the individual cells in the module for this purpose. Another requirement is for the slave to be able to measure temperatures. And again, their capabilities on this example demonstration board, to connect to off-board thermistors to be able to do that. From an algorithm point of view, we would love to measure the temperature of every single cell independently, but that requires an enormous amount of temperature sensors and wiring and expense. So, instead, most battery packs use only 1 or 2 temperature sensors per module, and some kind of an interpolation and extrapolation method to estimate the temperatures of the other cells in the module. The third function of a battery management system slave is to balance the amount of energy stored in every cell in the module. I've already mentioned balancing or equalizing a number of times, but we don't really get to study it in depth until course 5 in this specialization. But as a preview, each individual battery cell will have slightly different efficiency from one another and slightly different self-discharge rates, and so forth. And because of that, it's a requirement that we somehow be able to equalize the level of charge in individual cells, either by draining charge out of cells that have more energy than others, or by moving charge from cells having more energy to other cells that have less energy. This particular slave BMS design performs balancing by connecting a resistor in parallel to cell that happens to have too much charge. And this extra charge drains through that resistor and the level of charge then is depleted. And these resistors are on the top portion of this circuit board, all of the parallel components that you see there. A final important design requirement for BMS slave is to be able to communicate all of the information that it measures and collects back to the master, so that the algorithms can process this information in the master unit. And the particular solution shown here uses a serial bus, where the master can communicate over a daisy chain bus to the individual addressable components, or to all of the components at the same time using a broadcast message. The connectors that allow this are shown at the bottom to the left and to the right of the board, where one side has the connection from the neighboring board into this one, and then the other side connects out to the next neighbor, and finally, one of them connects to the master. A BMS master has certain responsibilities as well. The master must control the contactors or the high current switches that connect the battery cells, the battery pack to the load, and also disconnect the battery pack from the load. The photograph shows a prototype BMS master that we've developed in our research lab, and a production master would be much smaller and much neater than this. You must understand, this is for research purposes and has different requirements. But I include this photograph to enable me to point out a few components without too much difficulty. For example, the contactors are these high current switches I've mentioned a few times. In this photo, they are in the top right portion, where you see 3 white cylindrical elements. And each one of these is a contactor, and we'll discuss why we need 3 later this week. The master unit must also monitor the battery pack current. And in this particular design, there are 2 approaches to do so that the research team can investigate the advantages and disadvantages of the 2 approaches. One is called a current shunt method and the other is an inductive method, and you will learn about those later. And both of those are connected to the thick black wiring on the bottom right side of the battery pack. The master is also responsible for measuring isolation between the high voltage battery pack and the chassis of the load. And this is also accomplished in this prototype system, although the electronics to do so are less easy to point out. They're not really obvious from this photograph. The master must communicate with the slave, and this is done in our solution using a serial communication bus. The master must communicate with the host application, and these are done by again some communication buses that are connected with some of the ribbon cables that you see in the photograph toward the left. And finally, the master must control the thermal management system, which in our case is external to this box and must be done using external communication. One important benefit of a master-slave design is that many aspects of the design can be reused from one application to another. We don't have to redesign the electronics starting from zero, starting from nothing, every time we build a new battery management system for a new application. So, is it possible to reuse a slave design? And often, the answer is yes, assuming that the electronics used in the slave design are flexible in terms of the number of cells that they monitor, and assuming that the physical size of the slave design is something that can fit into different packages required by different applications. Maybe surprisingly, often the packaging size, the form factor of the slave turns out to be surprisingly important. So, even if the overall electronic design can be reused without any changes in different applications, it can be necessary to redesign the circuit board footprint to fit in different applications. If we anticipate that our product will have very high volume production, in that case, it might be to our advantage to optimize the slave design for that particular application, in order to save some cost in every slave unit that we sell. Also, you know that different lithium-ion cell chemistries have different voltages and different temperature ranges. And for example, a lithium iron phosphate battery cell often has a maximum voltage of around 3.6 volts, whereas others like NMC have maximum voltages around 4.2 volts. So, if our electronics are capable of measuring voltages between 0 and say 5 volts, we can accommodate different chemistries by simple software changes that anticipate these different voltage ranges. But, if our electronics can only handle a limited range, then we would need to redesign for every different chemistry. It turns out that a 5-volt voltage range is pretty common, and so, it's quite easy to design the slave electronics to be able to handle any lithium-ion chemistry presently on the market. So, it's often possible to reuse the electronic design for a slave board. So, we ask, is it possible to reuse the electronic design for a master board as well for different applications? And it turns out this is often more difficult. The master design needs to be more flexible. Different applications require different numbers of contactors and different types of contactors. And so, if we want a universal design, It has to be very flexible as to how many contactors it controls, and the ability to produce the different signals required to control those contactors. The current sensing solution that we use in the battery pack also requires some flexibility because we can use fundamentally different approaches to measure the electrical current. So, if we require a universal design, then our electronics must be able to control these different types of current sensor. There may be different ways to connect the battery pack charger depending on the application, and there may be different types of thermal management system as well. And so, it's possible to reuse the design of a master and a battery management system, but this can be accomplished only by incorporating quite a lot of flexibility using additional analog and inputs and outputs, and digital inputs and outputs that might be required in a special purpose design. So, we might consider a fairly generic design that we never actually implement. But when we implement a specific design, we take features from that generic design and keep those the ones that we require. And then, we omit the features that we do not require in a particular application. This brings us to the end of this lesson. And to summarize what you've seen, you've learned that high energy and high power battery packs require cells configured, both in parallel and in series. Safety and cost limit the number of cells in series. And losses versus cost give us a trade-off for the number of cells in parallel. So, the overall design is some kind of an optimization between the factors of safety and cost for the number of cells in series, and the losses for the number of cells in parallel. You've learned that battery packs are often built from smaller modules of cells. And this gives advantages with regard to how the modules are handled and how they're tested. And it tends to reduce the non-recurring or NRE engineering costs of building different battery management systems and packs for different applications. The fact that battery packs are often built with a modular design motivates building battery management systems with a modular design also, and is very common to see some kind of master-slave topology in a battery management system. The slaves handle the voltage measurement of the temperature measurement and balancing. And the master handles the battery pack current sensing, the isolation sensing, the contactor control, and thermal management. This modular design tends to make it easier to reuse the slave solution in many different applications. But there are greater challenges in reusing the electronic design of the master unless a lot of redundant components are built in to add quite a lot of flexibility that isn't usually needed in any particular application. So, in relatively high volume production, it usually makes sense to have a specialized master board for every application. And in some cases, it even makes sense to optimize the design of the slave board as well. But we also mentioned that the specialized electronics of a master implementation could be based off of some generic design, where you keep only the components from the design that are necessary and by eliminating the components that are not necessary in that application. So, that brings us to the end of this lesson, and we continue by looking at for the rest of the week, the requirements of a battery management system to be able to measure and control components inside of the overall battery pack. We now begin to look at the 5 requirement areas of a battery management system in more detail. For the remainder, our focus is going to be on requirement number 1, which is sensing and high voltage control. In this lesson, we are going to consider how to measure cell voltage. In a lithium-ion battery pack, it's absolutely critical to measure every single cell's voltage. The difference in voltage between cells is an indicator of their relative balance, and an indicator of how much they require equalization. And you will learn more about that in this specialization. Measurements of voltage are also required inputs to most state of charge and state of health estimation algorithms. And further, for safety purposes, it's critical that we know the voltage of every cell. Even if the voltage of a battery pack is within acceptable limits, it's possible for the voltage of individual cells to be outside of acceptable limits. And if I were to overcharge a lithium-ion battery cell by mistake, that can lead to thermal runaway as shown in the picture to the right. Thermal runaway happens when heat builds up in a cell which causes the separator to melt, which further causes an internal short circuit that leads to further heat buildup, and this reaction becomes self-sustaining. So in order to guarantee or ensure that we are not overcharging individual cells, we must know the voltage of every cell, and we cannot skip measuring any voltages in a lithium-ion battery pack. So how do we actually measure these voltages? At the most basic level, voltage is measured using a circuit that's known as an analog to digital converter. This technology has a number of commonly seen abbreviations such as ADC, or A or D, or A to D, or A to D spelled out. An analog to digital converter samples the voltage level at its input, and it converts that voltage level into a binary pattern of ones and zeros inside of a special purpose integrated circuit or inside of a microcontroller having a built-in ADC. The binary pattern is a digital representation of the voltage that it's measuring. There are several common analog to digital conversion architectures. One is known as a direct conversion or a flash technology. Electronically, this converter uses a bank of comparator circuits that detect whether the input voltage is above or below some internally regulated fixed voltage. So overall, this collection of comparators is used to determine and output the code corresponding to the voltage that's closest to any one of these comparator circuits. This technology is the fastest of all the ADC methods, and it's essentially instantaneous. But it's also the most expensive to implement because of the number of comparators and the number of fixed reference voltages that must be built inside of the converter. The second method for analog to digital conversion relies internally on really the opposite technology, a digital to analog converter. It turns out that it's relatively simple to build a digital to analog converter using some common components, some resistors, and an operational amplifier. There may be better approaches than that, but the main point is that it's simple to build a digital to analog controller, whereas it's more complicated to build an analog to digital converter. So the second analog to digital conversion approach guesses at what the voltage might be, and then outputs a voltage corresponding to that guess, using its digital to analog converter. It then uses a single comparator to see whether the voltage produced by the guess is above or below the voltage at the input that it's trying to measure. And by successive approximation, it keeps on this higher, lower guessing until it gets close enough to an estimate of the voltage it's trying to measure. This is a somewhat slow approach because of the need to repeatedly make these guesses, but it's also a very inexpensive approach to implement. The third approach is relatively modern and is adopted in many applications. It's known as a sigma delta or sometimes as a delta sigma approach. The method is somewhat similar to this successive approximation approach, in that it guesses what the voltage is and produces a voltage at its output corresponding to that guess. And then it uses a 1-bit flash analog to digital converter which requires only a single comparator to encode the difference between the approximation and the input it's trying to measure. Usually, the delta sigma approach uses very fast sampling in order to come up with sums and differences of the 1-bit ADC in order to very quickly approximate the input signal. So it successively approximates using a flash ADC at a very fast sample rate, and it's a very popular approach. Regardless of the method used for ADC, each of these is usually implemented in a specialized integrated circuit, or IC, because of the need to precisely match all of the resistances and capacitances and all of the components involved in making the circuit. And it's easier to match these components on side of an integrated circuit than it is using discrete components and an externally built circuit. It's also common practice to include analog to digital converters built into many microcontrollers. So battery management systems for small battery packs may not need any external circuitry outside the microcontroller itself for voltage measurement. When you're designing a battery management system and you must select an analog to digital converter for your design, there are several criteria that you must be aware of. The first that we will talk about is the resolution of the converter. The resolution of an analog to digital converter is the smallest change in the input signal that can be measured. It's the step size between consecutive converter output codes in voltage. So, consider an analog to digital converter that has m bits as its output. That means, it has 2 to the power m output codes. If these codes happen to be distributed evenly over the entire input range as is most common, then the range of input from the lowest voltage you can measure to the highest voltage you can measure, we will call EFSR, where FSR means full-scale range. If all of these are evenly distributed, then the resolution is the full-scale voltage difference divided by 2 to the power of m. For example, let's consider a converter that has inputs range from 0 volts to 5 volts. Suppose this converter also has 16 bits of precision such that m equals 16. Then the resolution of the converter, which we'll call Q, is computed as Q equals 5 volts minus 0 volts divided by 2 to the power of 16. The answer to this computation is 76 microvolts. The values I use in this example are typical of the better analog to digital converters presently available for battery management systems. So a resolution of 76 microvolts is a common value. The plot on the right illustrates this input-output relationship of an analog to digital converter. On the horizontal axis, you see the actual input voltage that's been normalized by subtracting the minimum voltage of the converter, and by dividing by the full-scale range of the converter. So that maps the minimum voltage to 0 and the maximum voltage to 1 on this axis. In this example, we are considering a converter that has 3 output bits, or m equals 3. So there are 2 to the m, or 8 possible distinct output codes, ranging from 000 all the way up to 111 in binary, and these are shown on the vertical axis. The blue line on the graph shows how the input voltage is converted into an output code. The input range is generally divided into 8 regions. And the converter rounds the input voltage to the closest voltage that is represented by an output code. So slightly negative inputs all the way up to slightly positive inputs get rounded to an output code of 000. And inputs that are a little larger than that get rounded to the code 001, and so forth. And this continues all the way up to the maximum measured voltage. And voltage inputs slightly smaller than the maximum value up to slightly larger than the maximum value are rounded to the output code 111. The input voltage distance between any one of these output codes is the resolution of the converter. So the output code changes anytime the input changes by this resolution voltage. So we could say that the smallest change in output corresponds to a single bit change in the least significant bit position of the output. So the resolution of an analog to digital converter is often called the LSB voltage, which stands for the least significant bit voltage of the converter. Another important consideration when choosing an ADC is its accuracy. Its accuracy has to do with the absolute difference between the reported value of voltage and the true value of voltage. And differences might arise due to several causes. One is due to the inaccuracy of quantization that we saw on the previous video, the rounding to the nearest output code. This means that there is an unmeasurable part of the true voltage, and that unmeasurable part has magnitude that is less than 1/2 of this resolution. The figure on the right illustrates this quantization error. There's a signal plotted versus time. So the horizontal axis is time, the vertical axis is value in the top plot. In the top plot, the blue line is the input voltage signal, and the red stair-step line corresponds to the voltage codes that are reported by the analog to digital converter. And you can see that the blue line has been rounded in every case to the closest voltage code that is available to the converter. But this rounding does not produce a perfectly accurate result. There's some difference between the quantized signal and the actual input signal. And this difference is called quantization error, and it is drawn in the plot on the bottom. So again, the horizontal axis is time, and the vertical axis now is the quantization error voltage. In this example, the analog to digital converter resolution Q is equal to 1 volt. And so the quantization error is limited to values between plus and minus 1/2 of a volt. A second source of inaccuracy in a converter is known as offset error. Offset is a constant difference, a constant bias between the ideal measured value and the reported measured value that spans the entire measurement range of the converter. Offset errors can be caused by biases in the electronics, either internal or external to the converter. A third source of inaccuracy of the converter is gain error. In the previous video, we saw the input-output relationship of an ideal conversion process. If the actual conversion process has different slope from what we've seen in this ideal case, that means that there is a gain error in the conversion. And this gain error is usually expressed as a %. Finally, the converter might have a nonlinear error. This is any departure from the actual and the ideal step widths in the conversion, and is often expressed in the number of analog to digital converter counts that are the worst case differences. There are several other considerations that we must take into account when we select an analog to digital converter. One is the effect of temperature. The offset and gain and nonlinear errors that we talked about on the previous video are all functions of temperature. And we must ensure that our solution provides acceptable performance within the entire range of temperature expected in the application. A second consideration is called timing jitter. Timing jitter is when the absolute time difference between samples made by the converter is not exactly constant. When we look at more detail on how we make models of lithium-ion battery cells, you will learn that we assume that there's an exactly constant timing between samples we make. These models will degrade in accuracy whenever the timing is not in fact constant. And so we will have some specification on the maximum timing jitter that we will permit in our converter. A third consideration when we are designing or using an analog to digital converter is related to something called aliasing. This is not so much a function of the converter itself, as it is a function of the fact that we are looking at a continuous time signal that only snapshots at discrete points in time, and not at every single possible point in time. In control theory and signal processing theory, there is something known as the Nyquist sampling theorem. This states that the sample rate of your conversion process must be at least twice the highest frequency found in the input signal. If we do not meet this criteria, then high-frequency inputs actually turn out to look like low-frequency inputs after their sample. The drawing in the video illustrates this. I draw a blue sinusoidal signal versus time. This sinusoidal signal has a frequency of 5 Hz. If we sample the signal very quickly, then we will be able to reproduce this 5 Hz signal with very high fidelity. The Nyquist sampling theory says that the minimum rate which we can sample the signal if we want to reconstruct it perfectly is 10 Hz. If we sample it more slowly than 10 Hz, then we have a problem. The yellow boxes on this diagram show what happens if we sample the signal at 7 Hz instead. And you can see that these yellow boxes correspond exactly to points on that blue signal sampled at a 7 Hz rate. We don't get enough samples per period if we sample this slowly, though, to be able to state with assurance that the input signal is 5 Hz. In fact, it looks to us as if the input signal might be 2 Hz instead. You see, the red dotted line on this graph is a 2 Hz sinusoid, and it passes exactly through the same yellow markers that were created by sampling the 5 Hz signal. So therefore, the actual 5 Hz signal is masquerading in our samples as a 2 Hz signal. Its aliasing is a 2 Hz signal, and that's why we call this phenomenon aliasing. One factor we have to our advantage when we are designing a sample radius, that battery cells have long time constants and they're quite slow devices. And that means that we usually don't need to sample the amp of voltages at a very high rate due to the dynamics of the battery cells themselves. However, it might be more important to sample the input voltage quickly if the external load has some very fast time constants. And then automotive application, for example, the battery pack is connected to a device called an inverter that drives the motor. And the inverter has power electronics inside of it that often have switching frequencies in the tens of kilohertz. And the switching can cause noise at those frequencies on this measured battery voltage. So by sampling more quickly than the battery dynamics themselves might dictate we need to, our algorithms for battery management may be able to help mitigate the effects of noise from the inverter and still provide good estimates of state of charge and state of health and so forth. Because high-power battery packs usually comprise many battery cells and series, it's not efficient to use discrete analog to digital components to measure all of the voltages and all of the cells. Instead, different manufacturers have created integrated circuits or chipsets for the specific purpose of aiding high-voltage battery management system design. These relatively low-cost measurement chips are used in modules or slave units close to the battery cells, and these measurement chips do not have any significant processing on board. Instead, they make the voltage measurements and they transmit those voltage measurements to a master unit. And the master unit does all of the processing for state of charge and state of health estimation and so forth. An advantage to delegating this analog to digital conversion task to specialized chipsets is that the integrated circuits can then be designed to implement the very difficult task of highly accurate voltage sensing with high common mode rejection with fast response in environments that often have high electromagnetic interference or ME, perhaps even high heat and high vibration. These chips are also often designed so that they can be placed in parallel for redundant and fault-tolerant designs. If different chips that are expected to provide exactly the same voltage measurement in fact produce quite different voltage measurements, then we can conclude that at least one of these chips is faulty. The master unit can then inform the application that there is a fault in the battery management electronics that must be investigated and repaired. There are a number of vendors that make chipsets to perform these voltage measurements, and some examples are Analog Devices, and Maxim, and Texas Instruments. In order to illustrate some common functionality of these chipsets, I've chosen to talk about the LTC6811 part. This part was originally designed by Linear Technology Corporation, and hence the LTC. But Linear Technology was acquired by Analog Devices, and so this part is now being marketed through Analog Devices. Each of the integrated circuits, each of the 6811 parts is capable of monitoring up to 12 cells in series in a module. And then multiples of this chipset can be placed in series in a daisy-chain slave architecture, so that overall, hundreds of cells in series in a battery pack can be monitored. In order to facilitate the connection of measurements from one slave to another, this chip has built-in isolated electronics for communication between the parts. That's also very highly noise immune that allows for very robust communication in noisy environments. This chip also supports both internal and external cell equalization circuitry, either using passive balancing or connected to an active balancing solution that is also marketed through Analog Devices. The chipset that can be powered by the battery module itself, meaning that we don't require an external power source in order to make it function, and that can be a huge advantage. And finally, this chipset that is able to measure up to 5 temperatures directly. It can also be configured with some external circuitry to measure more temperatures than that if that's what's required. The illustration on the slide shows a block diagram of the components internal to the 6811 chip. Everything in the orange box corresponds to electronics inside of the chip. And external to the component on the left we see the individual battery cells in series. The resistors and transistors drawn external to the 6811 are for balancing. The transistors inside the 6811 that connect to these external circuits control the balances. The external cell voltages are connected internally to two different multiplexers, analog multiplexers. And each one of these multiplexers is connected to a single sigma delta analog to digital converter. The 12 cells in the battery module then have their voltages measured 2 at a time and parallel, 1 voltage per multiplexer per converter. Therefore, after 6 conversion cycles, all of the cell voltages are measured. The other circuitry that's drawn on this diagram to the top of the 6811 has to do with communication across the isolated daisy chain mechanism between one component and another. Circuitry drawn on the bottom is used for interfacing with some general-purpose analog to digital inputs and outputs that can be controlled by the master BMS to measure temperatures or communicate with memories or any other number of functions. The example I presented on the previous video considers a component available through Analog Devices, but there are other components available on the market. And so how should you choose which component to use in your application? On this video, I present a few ideas for you to think about when you're making that decision. First, you need to consider how many cells are wired in series in your battery pack. And then you need to compare that against how many cells each integrated circuit from each silicon vendor is able to monitor. If your pack has a lot of cells and series, there can be advantages to choosing a chip that can monitor a lot of cell voltages at the same time. Another consideration is how many cells in total can be monitored using, however, many number of chips. The example I showed you is for the 6811 part that allows daisy chaining of individual monitoring chips. And seriously, you can monitor in total hundreds of battery cell voltages. But not every solution from every vendor allows for this, so you need to select a solution that's able to monitor all of the voltages that you require for your battery pack design. A third consideration is whether the chipset supports balancing. It's extremely helpful if you're able to control balancing for individual cells using this chipset instead of having to create additional electronics of your own to do so. Of course, The chipset must have the measurement accuracy that meets the needs of the algorithms you plan to implement in your battery management system. It must also be able to measure a sufficient number of temperatures for inputs to the battery management system algorithms. In order to minimize overall system cost, you may need to minimize the number of wires that are needed to communicate from one integrated circuit to another in between different slave units in the master BMS. And this might seem silly to you if you haven't performed this design before. But wires turn out to be quite expensive, and connectors between different parts in a battery management system further turn out to be quite expensive. And so minimizing the number of wires is a pretty significant concern. Finally, it's important to confirm that this chipset that you've selected is actually available. And what is the cost of the solution per cell in your design? And this might also seem like a silly consideration to you. But in my experience in the past, at least, there have been a number of silicon vendors that have announced products, and these products never actually made it to market and were never actually available. So it's important that you talk with a vendor to ensure that the quantity of components that you need will be available to you in a reasonable time. So in summary, in this section, you've learned that all battery cell voltages in a lithium-ion battery pack must be monitored continuously during operation. This is done using an analog-to-digital converter, which is generally built into a special-purpose integrated circuit that performs this function. When selecting an analog-to-digital converter, you must consider the resolution and the accuracy to ensure that both of these meet your design requirements. In order to monitor large battery packs, silicon vendors have produced specialized chipsets to perform all of the functions required. I showed you an example of one of these chipsets, the LTC6811. And you learned some general criteria to consider when selecting a chipset for your own design. And that concludes this particular topic on voltage measurement. The next thing that we are going to look at is, how do we measure other quantities in a battery pack for our battery management algorithms? In this section, you will learn how a battery management system measures temperature. It turns out that the operational characteristics of battery cells depend very strongly on temperature. For example, the electrical resistance of a battery cell is often quite low at warm temperatures and quite high at cold temperatures. And this means in part, that we can get more power out of the battery cell at warm temperatures because of the lower resistance than we can at cold temperatures. And so, the BMS needs to know what are the temperatures of its cells in order to be able to compute power limits and also to be able to accurately compute estimates of state of charge and state of health and so forth. It also turns out that the rate of degradation is a strong function of temperature. Battery cells tend to degrade much more rapidly at warm temperatures than they do at cold temperatures. And when the battery management system is controlling the thermal management system, it needs to know the temperatures of the battery cells in order to do so properly. There are exceptions to the general rule that degradation happens most quickly at warm temperatures. For example, at very cold temperatures, we can have extremely rapid degradation if we attempt to charge a battery cell. You will learn more about this in this specialization, when you learn about state of health estimation. But you will learn that a phenomenon known as lithium plating can happen, which very quickly degrades the cell and can even result in a safety situation. So it's common not to charge lithium-ion battery cells when the temperature is colder than about 0 degrees Celsius. We also measure temperature because some unexpected change in temperature can indicate a cell failure or some kind of impending safety concern. In an ideal situation, we would measure temperatures internal to every single cell in the battery pack. But that would require a temperature sensor somehow inserted into the packaging, and that's not really feasible. So we have to instead depend on temperature sensors that are somehow mounted external to some of the cells. And also, because temperature sensing is relatively expensive and because temperature differences across a well-designed battery module are relatively small, we often use only a few temperature sensors placed at strategic locations in a battery module or a battery pack, and we use a thermal model we have developed of our battery pack in order to interpolate and extrapolate among these measurements to come up with estimates of the temperatures at every cell location. In the previous section, you learned how a battery management system can measure voltage using an analog to digital voltage converter circuit. It turns out that there is no circuit that can directly measure temperature. Instead, somehow, we must come up with a means to convert temperature into a voltage that's related to that temperature, and then we measure the voltage using an analog to digital converter. And in this section, you will learn about two different technologies for measuring temperature. The first is to use a thermocouple. A thermocouple is made from placing two different metals in contact with each other, and these different metals actually form a kind of a miniature battery. A chemical reaction is happening at the surface of this bimetal barrier that produces a small voltage. The voltage that's produced by this thermocouple turns out to vary with temperature in proportion to the temperature difference between the thermocouple and some other reference temperature at a different point in the circuit. Now, this voltage difference is usually very small, on the order of microvolts, but it can be amplified and measured in order to form a voltage that I can convert into a temperature reading. A design challenge when using thermocouples is that we must have a calibrated reference temperature against which we are comparing the measured temperature, and some integrated circuits can generate this reference temperature internally, but otherwise, we need to have an externally calibrated temperature source, which is not feasible in a battery management system. So overall, in my opinion, thermocouples are best suited for laboratory testing when we can have all of the necessary temperature references and equipment on hand. But they're not especially well suited for production, battery management system designs. But while we are here, I show you a photograph that illustrates a thermocouple-based temperature sensor. The wand on the right of this instrument houses the two different metals inside this long pole. And this is connected through some standard wiring to the packaging on the left, and inside that packaging there are electronics necessary to produce the reference temperature and to amplify the signal and to produce a display of the temperature for the user to observe. An alternate approach to measuring temperature uses a component known as a thermistor. A thermistor is a special kind of resistor. All resistors turn out to have value that changes somewhat with respect to temperature, but most resistor designs are done such that this temperature variation is minimized. A thermistor, on the other hand, is a resistor that has been designed to maximize the change in resistance as a function of temperature. There are two varieties. One is called a negative temperature coefficient or NTC thermistor, and it has a resistance that varies inversely with temperature. The other kind is called a positive temperature coefficient or PTC thermistor, which has a value that varies proportionally with temperature. So if we were able to measure thermistor resistance, then we could infer from that measured resistance what the temperature must be, but we can't measure resistance directly with an electric circuit. Remember that we can measure only voltage directly using an analog to digital converter. So somehow, we must convert that resistance into a voltage that's measurable. And by the way, the photograph on the slide is simply showing a collection of thermistors, so you have some idea what they look like. So I need a way of converting resistance into a measurable voltage, and the most common way of doing this is to use a circuit that's known as a voltage divider circuit. I've drawn a schematic diagram of a voltage divider circuit on this slide, and in this circuit, the top resistor, labeled R1, has a resistance that is not changing very much with temperature, but the lower resistance labeled R therm has a value that is designed to change significantly with temperature, and this is the thermistor. The circuit is supplied with a constant known voltage, V, at the top of the circuit. And the analog to digital converter measures the voltage drop across the thermistor, which is labeled V therm. When we begin to analyze the circuit, the first thing we do is to compute the current that passes from the voltage source to ground. And our assumption is that the analog, the digital converter, draws essentially no current, and so we say that the current into that A to D device is zero. So then, we can use Ohm's law to say that the current through the two resistors connected in series is equal to the voltage drop across the resistors divided by the overall resistance, or I equals V divided by the sum of the two resistances. Again, by Ohm's law, we know that the voltage drop across the thermistor is equal to the current through that thermistor multiplied by its resistance. So, we can combine these two equations to find that the voltage drop across the thermistor is equal to the overall voltage V multiplied by a scale factor. and the scale factor is the thermistor resistance divided by the sum of the two resistances. Now, in the circuit, it turns out that there's always going to be current flowing from the voltage source of V to ground, and power is being dissipated through the circuit as I squared times R, where I has been computed already, and R is the sum of the resistances. This power is parasitic, we don't want to waste all this power, and so we would like to minimize then the amount of current that flows. So, we designed the value of R1 to be relatively high in order to minimize the current. But we also have to balance that requirement with the requirement of providing a measurable voltage at the thermistor. So usually, the value of R1 is similar to the thermistor resistance at some reference temperature like 25 degrees Celsius, and that's done in order to minimize the overall power loss but still, to provide a measurable voltage in the voltage divider. So our desire is to measure the voltage across the thermistor, and to use that voltage to be able to calculate the resistance of the thermistor. So we take the expression on the previous slide, and we rearrange it to solve for the resistance of the thermistor. When we do so, we find that the thermistor resistance is equal to R1 multiplied by a scale factor, and the scale factor is the voltage drop across the thermistor divided by the difference between the source voltage and the thermistor voltage. The data sheet that documents the specifications of the thermistor that you purchased will give you an equation that relates the resistance of the component to temperature, and this turns out often to be an exponential relationship like the one shown on the slide. In this equation, we see that the thermistor resistance is equal to some reference resistance R0 which is measured at some reference temperature like 25 degrees Celsius, and this reference resistance R0 multiplies an exponential term. And the exponential term has an argument that is related to the differences in reciprocals between the measured temperature and this reference temperature, where this difference is scaled by a device parameter beta. This equation is really fundamentally designed to work with temperatures in Kelvin, and so that 273. 15 factors converts Celsius temperatures into Kelvin temperatures for this equation to work properly. Let's look at an example of how this might work out in practice. In this example, I am using a negative temperature coefficient or NTC device that has a value of R0 equal to 100 kiloohms, measured at the reference temperature of 25 degrees Celsius, and it has a beta parameter equal to 4282. The plot that you see here shows resistance of the thermistor itself as a function of temperature. And you see that there is a very wide range, from over 2 megaohms at its highest point to essentially no resistance, as the temperature varies. In the second plot, I show what the measured voltage would be at the analog to digital converter if we use the thermistor in a voltage divider circuit, where the R1 value is equal to 100 kiloohms and the supplied voltage is equal to 5 volts. In extremely low temperatures, the thermistor resistance is very high and essentially, all of the voltage from the 5 volts sources dropped across the thermistor and none across R1, and so we measure a voltage that's close to 5 volts. On the other extreme, at very warm temperatures, the thermistor resistance is essentially zero, and so the voltage drop across the thermistor is essentially zero, and so most of the voltage will be dropped across R1, and so the measured voltage across the thermistor is essentially 0 volts. At the reference temperature of 25 degrees Celsius, the value of R1 and the thermistor resistance are equal. So, half of the voltage is dropped across each of the components, and so the measured voltage is half of 5 volts or 2.5 volts. And overall, the profile of measured voltage versus temperature has a sigmoidal shape, and when we plot it, we see that there's a fairly linear region between about 0 degrees and 50 degrees, and outside of that linear region, it does tend to curve more. So some very simplified designs rely on this linear shape if they don't require a very accurate temperature sensor, and they just fit a straight line to the central region. But if I want a more accurate calibration, I simply do a table lookup of the actual design values, which is also quite easy to do. So for this more accurate temperature measurement, we can invert the relationship in the second plot to compute the relationship shown in the plot on the right, the third plot. All I've done is to interchange the temperature and the measured voltage axis and replot the data that way, and this again gives me a lookup table so I can store a vector of measured voltages and a corresponding vector of temperatures. And anytime I read a voltage, I can look in that voltage vector and find the closest value, and then look up the corresponding temperature. So, for example, if we measured 4 volts, we can go to the lookup table and find 4 volts in the temperature, on the voltage axis rather, and then we draw this vertical line and notice where it encounters the blue line, and then the value of the blue line. By drawing a horizontal line, there is the point in temperature that we are measuring. So lookup tables are extremely efficient in terms of computation, even though they do require some memory to store all of these values. So to summarize this section, you've learned that we must measure and control cell temperature to preserve battery health, and to provide critical information to our algorithms that compute power and state of charge, and state of health, and so forth. It's generally too expensive to measure the temperature of every individual cell in a battery pack. So instead, we measure several temperatures inside of a module or inside of a pack using sensors placed at strategic locations. And then we use some kind of interpolation and or extrapolation scheme to estimate what the temperatures must be for every cell in the battery pack. There is no mechanism that allows us to measure temperature directly. So instead, we must somehow convert temperature into a voltage, and then we must measure that voltage using an analog to digital converter. And you learned about 2 different approaches. We can use a thermocouple with an amplifier, but there are some drawbacks to doing that involves complexity and expense. The other method would be the use a thermistor with a voltage divider circuit instead, and that's what's most commonly done. So that brings us to the end of this section on how to measure temperature. And as we continue on in this week, the next thing that we are going to look at then is how do we measure electrical current. And that's the topic of the next section. In our previous sections, you've learned how a battery management system can measure voltage and temperature. And now in this section, you're going to learn how battery management system can measure electrical current. Battery pack electrical current measurements are required in order to monitor battery pack safety, in order to ensure that excessive amounts of current are not flowing. They're required in order to log abuse conditions. And in addition, they're required by most state of charge and state of health algorithms, including those that you will learn about in the upcoming courses in the specialization. But remember that we cannot measure any physical quantity directly except for voltage. So we cannot measure electrical current directly. Somehow instead we must convert the current into a voltage signal and then measure that voltage signal using an analog to digital converter. And then from that reading and for what the current must have been. There are 2 basic approaches to doing this. The first approach is to use a resistive shunt and the second approach uses a Hall effect sensor. And you will learn about both of those approaches in this section. First, we look at the current shunt scenario. A shunt is a low-valued, but very high-precision, calibrated resistance that's placed in series with the battery cells and the load that they power. So usually at the negative terminal of the battery pack, between the negative of the battery and the negative of the load. The photograph on the slide shows a current sensing shunt. The large screw terminals on the top are connected, one to the battery pack, negative terminal, and the other one to the load, negative terminal. And all of the current passing through the battery pack passes through this shunt current sensor. The parallel plates between the 2 large screw terminals are what form the calibrated resistance. And when current flows through the resistance, Ohm's law tells us that there will be a voltage drop such that the current is equal to the voltage, divided by the known shunt resistance. If we were to use a large resistance, then we would also, however, waste a lot of power with this device, as heat. And that's not our desire. So we want to use a very small resistance. But when we use a very small resistance, the voltage drop across the shunt ends up being very small also. And so the voltage difference across the shunt sensor must be amplified before we sense it, and the calculation for current must be adjusted accordingly by dividing the measured voltage by the amplification factor before computing what the current must be. If we look at this shunt device in more detail, we notice that there are in fact 4 different connection terminals. As we talked about on the last slide, the 2 terminals on the top are connected, one to the battery pack and the other to the load. And that the overall battery pack current flows through those 2 large terminals and through the shunt device itself. All of this battery pack current passing through these parallel plates produces the voltage drop that we want to measure. And the resistance that's actually calibrated on this device is the value between the 2 small screw terminals, not between the 2 large screw terminals. And the sensing leads that we use to measure the shunt voltage are therefore connected to the small terminals and not to the large terminals. And so the large terminals don't have a calibrated resistance themselves, and the connection resistance of whatever connecting devices we put on them to connect to the battery pack and the load also don't have calibrated resistance. And that could be quite significant. It can quite significantly bias our calculations if we were to measure across the large terminals. So we measure across the small terminals instead. And it's very important to connect a shunt this way. This connection style is called a Kelvin connection, and it enables what is known as 4-wire voltage measurement. We assume that essentially no current is drawn by the analog to digital converter that's connected to the small screw terminals. And therefore the wiring between the A to D and the small screw terminals has no voltage drop over it. And so we are truly measuring the voltage drop across only that calibrated resistance. If we were instead to connect the voltage sensing wires to the large terminals, we would be measuring the voltage drop across the calibrated resistance plus the voltage drop across the screw terminals in that connection. And a large current flows through those. And so there would be a significant I times R voltage change across the large terminals that would really interfere with us being able to get good measurements of what current is. We would make serious miscalculations. So to summarize the current sensors using shunt sensing mechanism before we look at the Hall effect sensor. I'll make a few comments here. So you've seen that in order to use a shunt sensor we absolutely must use this 4-wire connection, otherwise our measurements will all be wrong. When we compare this method of sensing to the Hall effect method that we are going to talk about very soon, we'll find that an advantage to using the shunt sensor is that there is no built-in offset at zero current using a shunt. In other words, the voltage drop at zero current is I times R or 0 volts. And so a shunt sensor is good to avoid drift in certain kinds of state of charge estimation algorithms. In particular, in the 3rd course in the specialization, you'll see that there's a simple method to estimate state of charge. That's called Coulomb counting. And what it does is to integrate the current sensor measurements. But if there's a constant offset in the current sensor measurement, I'll be integrating that offset over time and I will get ever increasing estimation error, and that's of course really bad. So we desire a current sensor that has no offset if at all possible, and the current shunt in fact does not have offset. So that's really good. But we do still have to be careful because even though the shunt has no built-in offset, the amplifying circuitry and the analog-digital conversion circuitry may have some offsets. So we still may need to calibrate some offset out. There's just going to be relatively little of it to calibrate out. When we compare this type of current sensor to a Hall effect, it also has a disadvantage in that the shunt is not isolated electrically from the battery pack. And in many times, this is a requirement that the battery management system electronics be electrically isolated from the battery that they're managing. And if that's the case in your particular application, you will require extra circuitry to isolate this current shunt from your BMS electronics. So an example is an automotive application where traditionally, the BMS is powered by the 12-volt lead-acids battery in the vehicle. And the other electronics, the motors and so forth are powered by the high-voltage battery pack. And so if there was a loss of electrical isolation between the BMS and the high-voltage battery pack, that means that there is a loss of isolation between the 12-volt system and the high-voltage battery pack. And if you know how standard automobiles are constructed, the 12-volt system is actually physically connected to the chassis of the vehicle. And so if I don't have isolation between the high voltage and the 12-volt, I also don't have isolation between the high voltage and the chassis. And so that's a safety consideration because someone touching the chassis could shock themselves. And we don't want that. And so this isolation is a requirement that's not built in that we would have to add. And a design consideration when using a shunt is that we desire to have a very low shunt resistance in order to minimize power losses. But regardless of whatever resistance we end up choosing, there will be some power loss. And this power loss will result in heat buildup, and the heat buildup must somehow be removed by our thermal management system, so it places additional load on that system. Finally, you've seen that we need to amplify the shunt signal in order to get a measurable voltage. And anytime there's amplification, that introduces the possibility of amplifying random electrical noise in the circuit. And therefore it can be important to shield the wiring between the shunt sensor and the amplifier from this electromagnetic interference. Now we look at the Hall effect current sensing method instead. This is based on a principle from electromagnetics where we find that if a coil of insulated wire is wrapped around a primary current carrying wire, that this primary current carrying wire induces an electrical current in this coil. Even though there's no electrical connection whatsoever, it's done through the electromagnetic fields that are built up when current is flowing through a wire. Hall effect sensors measure this induced current in the secondary coil and use that to infer what the amount of current passing through the primary wire must have been. So in the photograph on the right hand side of the slide, I show an example of a Hall effect current sensor. And I hope you can see there's a large oval opening in the sensor toward the upper right hand side. And the large current carrying conductor would be inserted through this opening, and there's no electrical connection whatsoever. We just pass the wire through the opening. And inside of this packaging for the Hall effect sensor, there's actually a coil that wraps around that opening, and there's further electronics inside of the package that measure the current going through this coil and produce an output voltage that's somehow proportional to that current to be measured by the battery management system. And that's illustrated schematically on the right. At the bottom you can see the current carrying wire going through the center of the coil, but it's not electrically connected. And the coil wrapped around the secondary, the voltage across that coil, or the current through that coil, rather, is measured and is conditioned. And makes a voltage proportional to that current for the battery management system to measure, as well. We can summarize some of the design considerations for a Hall effect current sensor that we need to think about. One advantage when we use a Hall effect sensor is that it's automatically isolated electrically from the battery pack current. Because there's no electrical connection whatsoever between the primary current carrying wire and the sensor. So we don't require any isolation circuitry when we're measuring battery pack current. However, anytime we use electromagnetics, there is a physical phenomenon that we can encounter, known as hysteresis. And magnetic hysteresis causes the present measured voltage to be a function not only of the present instantaneous current going through the primary, but also somehow a function of past current that went through this primary current carrying wires. So there's a history somehow embedded in the present measurement, and in some case it's possible to purchase Hall effect sensors that have feedback circuitry that tries to eliminate this history as much as possible to give you as clean a present instantaneous measurement as possible. But no matter how good a job you do with this conditioning circuitry, there will always be some amount of hysteresis in your measurement that you have to deal with. So this hysteresis means that a current reading after charging your battery pack for a while will be different from a current reading after discharging a battery pack for a while, even though the current might be exactly the same at this moment in time. And in particular, if the battery pack is resting, and we should be measuring zero current, I will be actually measuring some value above 0 or less than 0 depending on whether I've recently been charging or discharging. And that's a problem if I'm integrating the current sensor in order to provide a state of charge estimate, then I will have this offset that will cause increasing error over time, and that's not desirable. So one possible solution is to measure current from the Hall effect sensor when the battery pack is disconnected from the load and we know the current is 0. And then to use that as our default 0 measurement and subtract that value from all future measurements. But unfortunately, there's bias is not a static thing. It actually changes with time, and it drifts with time, and it changes with temperature also in often unpredictable ways. So even if we come up with a clever scheme, somehow to zero out this offset by subtracting an estimate of the offset, there's always going to be some error in the reported current and bias in the reported current that changes with time and with temperature. And this causes all kinds of problems with the number of battery management system algorithms, especially state of charge estimation. So if we are to use a Hall effect current sensor, some kind of compensation is necessary. And it's often also necessary to try to estimate the DC bias, and to subtract that out from measurements in our algorithms. Because of this additional complexity to the algorithms and the uncertainty that this adds to our estimates, I personally don't prefer Hall effect current sensors. But you'll still find them in many commercial products, mostly because their built-in electrical isolation makes them very attractive to electronics designers. So in summary, we must be able to measure battery pack electrical current in order to monitor battery pack safety, in order to log abuse conditions, and in order to inform state of charge and state of health algorithms. You learned about two different methods that might be used. We may either use a current shunt or a Hall effect sensor. Both of these methods have their advantages and disadvantages, and both are actually in common use. And when you're designing your own battery management system, you'll need to evaluate the advantages and disadvantages of both, to come up with the correct decision for your own particular design. That brings us to the end of this particular lecture, this lesson topic. And it brings us to the end of our three main sensing requirements of sensing voltage, and current and temperature. And from now on, for the rest of the week, we look at some other high voltage measurement and control aspects of measuring isolation and contactor control and thermal management system control, as well. And that's what we start to do next. In recent topics, you've learned how a battery management system can sense the physical quantities of voltage and temperature and current that it must know in order to safely operate the battery pack and to execute the algorithms that you'll be learning about later in this specialization. In this section, you will learn for the first time about how a battery management system must control something instead of simply measure or sense something. Specifically, you will learn how a battery management system controls its contactors. When a battery pack is not in use, its internal high voltage bus must be completely disconnected from the load at both the positive and the negative terminals. And it does this to prevent a high voltage shock hazard. Now, to be able to disconnect both terminals from the load, we require some kind of electronically controlled on-off switch that's capable of conducting large levels of current when it's turned on. One of these switches is used to connect the positive terminal of the battery pack to the load. And the other, to connect the negative terminal of the battery pack to the load. These switches must be electronically controllable, of course. And a device that can perform this operation is known as a relay, or more often as a contactor when we are using this device to control large amounts of current. And there are some internal differences to how a relay and how a contactor work. But both of them are high current capable devices, they're on-off controlled switches. The photograph on this slide shows an example contactor. And the physical size of the device, to give you some reference, is maybe about the size of your fist. Maybe a little smaller than that. The red and the black wires that you see in the photograph are the low voltage, low current wires that control the contactor. The screw terminals on the top are where we connect the high current carrying wires. When we apply a voltage to the red and black wires, that closes the contactor, and it makes a connection electrically between those two screw terminals and allows current to flow. When we remove the voltage from the red and black wires, that opens the contactor and it opens up, or removes, the connection between the screw terminals and that causes current to stop flowing. When we connect the battery pack to the load, it's not simply a matter of closing both contactors and then operating. We actually have to be quite careful when we connect a battery pack to most loads that we might encounter. And the reason is that many loads have a high capacitance to them. For example, in the vehicle application, the load of the battery pack is the motor controller, otherwise known as an inverter. And this inverter operates semiconductor devices and switches them on and off at very high frequencies, which would tend to put very high transients on this voltage bus. And that can cause damage to the battery pack that we don't desire. And so the inverter also has large capacitors inside of it to smooth out these transients so that when the motor is operating, the battery pack does not experience this high level of noise, caused by the load that it's connected to. So that's a good thing. But on the other hand, If I started with a motor controller whose capacitors were initially at 0 volts charged, and I wanted to connect a high voltage battery pack and I connected both the positive and the negative terminals at the same time, what would happen would instantly an enormous amount of current would flow out of the battery pack to try to charge the capacitors in this load. This enormous amount of electrical current has the potential to cause arcing inside the contactors and to weld them closed. And after that point they would never be able to physically be opened again. They'll be physically damaged and it could even blow a fuse in our battery management system. So any practical battery management system for a high power application uses not 2 contactors, but 3, where the third contactor is known as a pre-charge contactor. And in this section, you will learn how the contactors are controlled when the battery pack needs to connect to the load and how they are controlled when the battery pack disconnects from its load. The drawing here shows how a battery pack is connected to the external bus and the location of 3 contactors in this overall schematic. To the far left you can see the series connected battery stack. And I've drawn a fuse in the center of this battery stack. So that if the fuse were to blow, the pack would be divided into 2 parts. And the overall pack voltage then would be divided essentially in half. So if the technician were to open up the battery pack, the maximum voltage that could be encountered would be half of the battery pack voltage. So the fuse is placed where it is to minimize the maximum voltage that would be encountered by the technician. The fuse is put there for safety reasons. The boxes are symbols that depict the contactors, and at the top of each symbol, you can see 2 terminals with a thick line drawn above it. In this diagram, none of these thick lines or bars are connected to the terminals, and so all of the contactors are in an open state. When the contactor is in an open state, that means that the left side of the contactor is electrically disconnected from the right side. In each of these contactor symbols, you can also see that there's a coil drawn at the bottom. And this is the control mechanism for the contactor. When the coil was activated, the contactor closes, and a connection is made between the high current terminals. When the coil is deactivated, the contactor opens, and the high current terminals are then disconnected. The thick lines in the diagram shows the parts of the circuit that are presently activated. And the diagram shows a battery pack at rest, so all of the connectors are open, all the contactors, rather, are open and the only activated connections are to the left of the contactors. The load is completely disconnected from the battery pack at this point. Now notice that I have activated the left branch of all the contactor coils, but the right branch of only the negative contactor. This connects the negative terminal of the battery pack to the negative terminal of the load. But at this point, the positive terminal of the battery pack is still disconnected from the load. The next step is to close the pre-charge contactor. So far, I have not changed this diagram. To close the pre-charge contact here, I need to activate the right branch of its coil circuit. And when I do that, the contactor closes and a pathway is formed between the positive terminal of the battery, through the pre-charge contactor, through the pre-charge resistor to the positive terminal of the load. So let's do that. At this point, current flows from the battery pack through the pre-charger resistor to the load. The capacitance of this load is able to charge because of this current flowing. But the resistance of the pre-charge resistor limits how quickly we charge that capacitor. And that ensures that the contactors don't fuse, that there's no damage caused to them. The battery pack current is limited by this pre-charge resistor. If all goes according to plan, the capacitive load is quickly charged up and we can move on to the next step. But for fault tolerance, it's important to check to see whether things are going according to plan. So one thing we can do is to monitor the temperature of this pre-charge resistor. And if the temperature becomes too high, then the load may have some short circuit inside of it and may draw in too much current. So if that's the case, we can deactivate the pre-charge contactor and deactivate the negative contactor and disconnect the battery pack from the load. We can also monitor the bus voltage and the pack voltage. If these voltages do not converge quickly enough to the same value, then again the load may have some kind of a short circuit fault and the pack will disconnect. Or instead of monitoring the load voltage in addition to the battery pack voltage, we can monitor one of the voltages, usually the battery pack voltage, and the load current, which we have to do anyway. So we would then disconnect, we would consider that the capacitive load was fully charged when the current going to the load was essentially zero. And this might be a better approach since we already have a battery pack current sensor and are already measuring the battery cell voltages, so we don't need to add an additional sensor to do this. If the precharge current does not approach zero quickly enough, the load may have a short circuit and the pack should disconnect. The third step is to close the positive contactor. Again, I've redrawn exactly the same picture from the previous slide as a starting point. If we determine that the bus voltage and the pack voltage have become close enough quickly enough, then we can close the high current pathway. Alternately, if the precharge current has approached zero quickly enough, we can close this pathway. We do so by activating the right branch of the coil of the positive contactor. At this point, all three contactors are closed, so the negative terminal of the battery pack is connected directly to the load. The positive terminal of the battery pack is connected through the precharge resistor to the load, but it's also connected directly through the positive contactor to the load. And because the positive contactor has essentially no resistance, this precharge path, even though it's still active, carries essentially no current. The load is now connected directly to the battery pack through two low resistance contactors for a single low resistance pathway. The final step after the positive contactor is closed is to open the precharge contactor. We do this by deactivating the right branch of the coil for the precharge contactor. Notice in the diagram, the precharge pathway is now deactivated, but there's still a low resistance pathway for current to flow from the battery pack to the load. And at this point, the normal pack operation starts. It's interesting to consider what we should do when we're shutting the pack down. How should we disconnect the battery pack from the load? And the answer is not as clear. If the load is actively drawing power from the battery pack and I abruptly disconnect, then arcing might still occur across the contactor as I'm trying to open it up. And that might still weld the terminals together internal to the contactor and cause the contactor to be permanently closed, even though I'm trying to open it. So one possibility when shutting the battery pack down is to activate the precharge path, once again, to shut the pack down in the reverse order from which I started it. But again, if current is being actively drawn from the battery pack set, and I were to disconnect the battery pack in an emergency situation, then there might be more current through the precharge resistor than that resistor is graded for. And consequently, this resistor might turn into a fuse and might be destroyed. But remember that the entire reason for requiring the precharge circuit in the first place is because the load is often capacitive. That means that the load has some amount of energy stored inside of it. So if all the contactors were simultaneously opened in some kind of emergency setting, the capacitor in the load stores enough energy that it's likely to supply the load for a period long enough for the contactors to open completely to prevent arcing from happening and to prevent damage. So most likely the battery pack can be disconnected from a capacitive load simply by opening all of the contactors without an elaborate shutdown procedure. To summarize what you've learned in this lesson, you've seen that there is a need to be careful when connecting a battery pack to a load when we are powering the battery pack on. It's very common for the load to be capacitive in nature. And for that kind of scenario, a precharge path is needed in order to charge the load somewhat slowly before the main contactor is closed. This imposes a need to be able to measure both the battery pack voltage and the battery bus voltage. Or to measure the battery pack voltage and current through the battery pack. And that saves the need for additional sensors. And finally, we also discussed a procedure to follow when powering down the load, and that this procedure was maybe not quite as clear as the one to follow when powering up the load. But nonetheless, you could experiment with both and see which works best for your application. So that brings us to the end of this lesson on how to turn on your battery pack. With this section we continue to investigate requirement 1 of battery management systems, which have to do with sensing and control. The particular aspect that we are going to look at now has to do with sensing the presence of a ground fault, otherwise known as an isolation fault. The primary concern that we have has to do with safety. We ask the question, is it safe to touch one external terminal of the battery pack and the vehicle chassis at the same time? And one possible application has to do with when a vehicle is being serviced. If I open up the hood of the vehicle as shown on this picture, and if I were to touch one terminal of the battery with one hand and to touch the chassis of the vehicle at the same time with the other hand, would I be safe? Another application would have to do with, if I were in an accident and somehow the electronics and the battery pack structure were compromised, would it be safe for an emergency responder to touch the chassis of the vehicle? Or you as an occupant, would it be safe for you to touch the chassis as you're trying to exit the vehicle? The high voltage battery should be completely isolated from the chassis, so there should be no problem. And notice that this is quite different from how the 12-volt system is wired in a standard vehicle. In a standard vehicle, the positive terminal from the 12-volt battery is wired independently to everything in the vehicle that requires power. But the ground of the 12-volt battery is wired directly to the chassis. And this is done to eliminate the need for running ground wires to every component in the car. It saves wiring. And it's safe to do so because 12 volts from the 12-volt battery does not have sufficient potential to cause significant injury or harm. It's not safe to do the same thing with a high-voltage battery, so neither terminal of the high-voltage battery should ever be connected to the chassis of the vehicle. There is a safety standard that dictates the requirement for isolation. The Federal Motor Vehicle Safety Standard, or FMVSS, says that isolation is considered sufficient if less than 2 mA of current can flow when I connect the chassis to either the positive terminal directly or to the negative terminal directly, using a direct short circuit. This is because it's believed that 2 mA of current is less than but close to a lethal threshold. So for worst case analysis, we consider that the resistance of a person might be 0, and if a person were to connect using their body, these 2 points, we would want less than 2 mA of current to flow. So how to measure isolation? We set up the problem by drawing the schematic diagram shown on the right. And at the top of the schematic you can see the high voltage battery and its positive and negative terminals that could be connected to a load. And at the bottom of the schematic, we see the chassis of the vehicle. And ideally these are completely isolated electrically from each other, no connection whatsoever. I modify the diagram now a little bit to show between the high voltage battery and the chassis I've added 2 voltmeters and 2 resistors. The resistors model the resistance between the negative terminal in the chassis and between the positive terminal in the chassis. These are not physically present. We don't physically add resistors because that would break isolation. These resistors are shown in the circuit to model whatever resistance is actually present. And ideally that resistance is infinite. I also draw these voltmeters, V1 and V2. And we will actually measure these voltages at some point in our algorithm for checking for isolation. Since we wish for both resistances to be infinite, the worst case resistance is going to be the smaller of the 2 resistors. So we define something called an isolation resistance, Re, to be the minimum of R1 and R2. And since we require that less than 2 mA of current can flow, if there's a direct short from one side of the battery to the chassis ground, that means that the remaining resistance must limit this current flow. So by Ohm's law, the isolation resistance must then be greater than the battery voltage divided by 2 mA. In other words, it must be greater in magnitude than 500 times VB. VB is the battery voltage. So our objective is going to be to somehow measure this isolation resistance, the smaller of these 2 resistances. We don't care about the larger one, we just care about the worst case smaller one. And to do so we begin by measuring the 2 voltages shown in the diagram using a high impedance analog to digital converter that has an internal resistance that's specified usually to be greater than 10 megaohms. You see, when we are placing these voltmeters in the circuit, technically speaking we are breaking the isolation that we are looking for. We are making a pathway between one terminal of the battery pack and the chassis of the vehicle. But because we've specified that the resistance of the voltmeter must be greater than 10 megaohms, we ensure that less than 2 mA of current will flow for most batteries, unless the battery voltage is extremely high. And so, this is not breaking isolation according to our specification, by placing this voltmeter in the circuit. Also notice the polarity indicated on the voltmeters. Both voltages are defined to be positive values. And so when we look at the equations on the upcoming videos, keep that in mind. To continue with the analysis of this circuit, first copy the circuit diagram from the previous video on the top. But I've also redrawn the circuit in a slightly different but equivalent way on the bottom. And if you spend a minute and examine both of these diagrams, you will see that all of the connections are exactly the same. But the diagram on the bottom makes it a little bit more clear that the two resistances form a voltage divider across the battery voltage. Similarly, we see that the sum of V1 plus V2 must be equal to the overall battery voltage. Our objective is to find the smaller of the two resistances. And in a voltage divider, the lesser of the two measured voltages corresponds to the smaller resistor. So if V1 is less than V2, then we must find R1. Otherwise we must find R2. In the next few slides we are going to talk about a method that we can follow in order to do this. But before we do so, I first note that we can write that the quotient of V1 divided by R1 is equal to the quotient of V2 over R2. We find this to be true by using Ohm's law and recognizing that I1 must be equal to I2 since that's the only pathway through which current is flowing. And we are going to use these identities in the mathematics we use to solve this problem. We are going to consider two independent cases. In one case, we have determined that V1 is less than V2 and so we must find R1. And the opposite case would determine that V2 is less than V1 and therefore we want to find R2. But let's start with the first case. Our next step is to insert a known resistance R0 between the battery and chassis using a transistor switch to close the circuit as shown in the diagram. So, once again, this is going to break strict isolation because we have intentionally made a pathway between the positive terminal and the chassis of the vehicle. However, if we choose this resistor, R0, to have a large enough resistance, then we don't actually violate the requirement of less than 2 milliamps of current flowing. So this requires that the resistance R0 be much greater than 500 times the battery voltage. After we've inserted this resistance, we measure the new voltage V2'. By Kirchhoff's current law, we know that the current flowing through R1 between the negative terminal of the battery and the chassis must equal the sum of the currents flowing through R2 and through R0, that we've now added to this circuit. So by Ohm's law, the current through R1 is the voltage drop across R1 divided by its resistance. The voltage across R1 is equal to the battery voltage, minus this new measured voltage, V2'. So the current passing through R1 is equal to the battery voltage, minus V2', all divided by R1. The current through R2 is equal to its voltage drop divided by its resistance which is V2' divided by R2. The current through R0 is its voltage drop divided by its resistance, or V2' divided by R0. Therefore, we have this equation that have shown that basically says that the current through R1 is equal to the sum of the currents through R0 and R2. Or VB minus V2' all divided by R1 equals V2' divided by R2 plus V2' divided by R0. We continue the analysis of this equation by substituting the fact that the battery voltage is equal to the previously measured V1 plus V2. And the fact that R2 is equal to R1 times the quotient of V2 divided by V1. We find that V1 plus V2 minus V2' divided by R1 equals V2' divided by R2 plus V2' divided by R0. We can rearrange this by making the substitution for R2 that we have in the last bullet point on this slide. And we find that this is equal to V2', multiply the quotient of V1 divided by V2, all divided by R1, plus V2' divided by R0. So we are going to start with that equation and continue on the next video. So on the last video we concluded with this relationship. And to proceed, we combine all the terms that include resistance R1, which is the term on the left minus hand side of the equation and the first term on the right minus hand side of the equation. We bring them all to the left side of the equation by subtracting the term on the right minus hand side. And when we do so, we find this result, that V1 plus V2 minus V2' times the quotient of V1 over V2, all divided by R1 as V2' over R0. We rearrange this equation, The first thing we do is we take the reciprocal of both sides and then we solve for R1 by multiplying both sides by what's the numerator of the left minus hand side as written, but what would be the denominator after taking the reciprocal. We do some rearranging and we have a final answer that you can see here, that R1 equals R0 times the scale factor. And the scale factor is 1 plus V1 over V2 times quantity V2 minus V2 prime, all divided by V2 prime. We make this calculation. We find R1 and our final conclusion is that the battery pack is sufficiently isolated if this isolation resistance R1 is larger than 500 times the battery voltage. And that the battery pack therefore is not sufficiently isolated if this condition is not met. So what we've seen in the last few videos is a method for determining the isolation resistance if the initial measurement of V1 was less than the measurement of V2. And the procedure for determining the isolation resistance turns out to be essentially the same if the opposite condition is true. Except now, we must find R2 in the circuit instead of finding R1 in the circuit, because that will be the limiting value. To do so, we insert a large known resistance, R0, between the battery's negative terminal and the chassis using a transistor switch as shown in this diagram. We now measure the voltage difference between the negative terminal and the chassis, which is labeled here as V1 prime. By Kirchhoff's current law, we again say that current through resistance R2 is equal to the sum of the current through resistor R1 and the current through R0. And using Ohm's law, we convert these equations into voltages divided by resistances and we achieve this equation that you see here. That the battery voltage minus V1 prime all divided by R2 equals V1 prime over R1 plus V1 prime over R0. Our next step, once again, is to substitute the identity that the battery voltage is equal to the sum of the originally measured voltage as V1 plus V2. And we also substitute that R1 equals R2 times the quotient of the two voltage from the earlier identity, as well. And we achieve this equation here, which is very similar to what we saw in the opposite case. Here, we see that V1 plus V2 minus V1 prime, all divided by R2 equals V1 prime, multiplying V2 divided by V1, all divided by R2 plus V1 prime over R0. To continue, we start with this equation on the next video, copied exactly. And we combine all of the terms that include resistance R2 and we bring them to the left side of the equation as you can see here. And again, we take the reciprocal of both sides of this equation and we solve for R2. And the final result, you can see, is that the isolation resistance R2 equals R0 multiplying a scale factor, where the scale factor is 1 plus V2 over V1 times V1 minus V1 prime all divided by V1 prime. Once again, we conclude that isolation is sufficient if the isolation resistance R2 is bigger than 500 times the battery voltage and that isolation is not sufficient if that condition is not met. That we must maintain isolation between the high voltage battery pack and the chassis of the vehicle. Isolation is considered sufficient if less than 2 mA of current can flow if a direct short circuit were to be introduced between either of the battery terminals and the chassis. You learned how to conduct the Federal Motor Vehicle Safety Standard, or FMVSS, procedure for determining the isolation resistance, RE, for the battery pack. And the bottom line, you learned that if we follow this procedure, we consider that isolation is sufficient if this resistance is bigger than 500 times the battery pack voltage. That brings us to the end of this topic. And there is one more topic remaining when we look at the measurement and control aspects of requirement 1 of a battery management system. And that's what we are going to look at in the next section. So in summary, in a vehicle application, you've learned the final topic that we look at, that relates to requirement 1 of the battery management system is that of thermal control. And this is not a major focus of this specialization. So I am not going to go into a lot of detail, but there are some important and relevant points to mention, and that's what this lesson is all about. The temperature of a battery pack has some fairly significant impacts on safety as well as on the lifetime of the battery pack. Generally, Lithium-ion battery cells last longest if they're maintained in a temperature band from about 10 degrees Celsius to about 40 degrees Celsius during use. A good rule of thumb is that if you as a human being are comfortable at a particular temperature, then the battery pack is also comfortable at that temperature. In other words, if you feel too cold, then it's probably too cold for the battery pack to perform well. If you feel too hot, then it's probably too hot for the battery pack as well. The battery pack can certainly survive colder and warmer temperatures, but you get the maximum performance and a maximum life out of the battery pack if you maintain it in that kind of a temperature band. The figure on the left of this slide illustrates the safe operating window of lithium-ion battery cells as a function of cell voltage and of temperature. On the horizontal axis you see cell voltage. The safe operating range is going to be different for lithium-ion cells of different chemistries, but this is generally between about maybe a little over 2 volts up to maybe a little over 4 volts. The vertical axis is temperature in degrees Celsius. And the safe operating window extends maybe from about -30 degrees Celsius up to about 60 degrees Celsius on this axis. Again, there are some variations depending on how the cell is manufactured and what additives are placed in the electrolyte, some different things like that. But roughly speaking, this is the safe operating window of lithium-ion cells in general. If the cell voltage becomes too low, then the current collector on the negative electrode begins dissolving into the electrolyte. And remember that this is a copper foil. And so copper from this current collector dissolves into positively charged copper ions in the electrolyte. And these try to compete with the positively charged lithium ions in the electrolyte to cycle back and forth through the battery cell, just as the lithium does. Now these copper ions are usually too large to intercalate into the active materials of either electrode. And so instead, they plate metallic copper onto the surface of the electrodes. And this causes a metallic annealing site to form. And once one of these sites has formed, it's easier for any other trace metals there are in the electrolyte to form on this annealing site. And to make long, thin, metallic dendrites that can grow across the separator and cause a short circuit between the two electrodes of this cell. So worst case, undervoltage can lead to short circuits and to thermal runaway. On the other hand, if I overcharge a battery cell, that can cause positive electrode breakdown. Remember that when we charge a cell, lithium moves out of the positive electrode. And remember that in some electrodes, there's this layered crystal structure that can collapse if too much lithium is removed. So overcharging causes material breakdown in this electrode and quite severe capacity loss. If I overcharge a battery cell at cold temperatures, lithium comes out of the electrolyte in ionic form and it'll actually plate solid metallic lithium under the surface of the negative electrode. It's called lithium plating. This removes lithium from circulation, so it causes capacity loss. And it also causes dendrites to form and can lead to short circuits as well. Those are some of the primary causes. They can also lead to secondary effects. For example, if I overcharge a battery, it can lead to temperature rise. And that itself can cause the solid electrolyte interface layer, a film layer that grows on the negative electrode particles to passivate them, to break down and expose fresh graphite to the solvent in the electrolyte, which causes more solid electrolyte interface layer to grow. And this reduces the amount of cyclable lithium and decreases the capacity of the battery cell. And just the very active this formation and growth of the solid electrolyte interface, can cause temperature rise. And so temperature rise causes growth, which causes temperature rise, and you see that you are having a problem. At some point the separator can melt and this could lead to short circuits between the negative and the positive electrode particles. And that short circuit causes large amounts of current to flow, which causes additional temperature rise. This can cause the electrolyte to begin to break down and to form gases and to build up pressure inside the cell. Some of these gases are flammable, and if they're released to the environment, if the cell packaging fails, that can lead to external fires also. As temperature increases, this possibility of venting increases and the problem is getting worse and worse. You can tell it's accelerating. The cathode materials, the positive electrode materials, often contain enough oxygen, they're generally oxides. And there's enough oxygen in the material itself that once a fire has started, that the fire is self-sustaining. And even in a vacuum the cell will continue to burn because of the oxygen that is in the positive electrode. And this is a condition called thermal runaway and must be avoided at all costs. So it's also worth noting that it's not only the maximum or minimum temperature of the battery pack that matters. It's also important to keep a relatively uniform temperature across all of the cells of the battery pack. The rate of aging depends on the temperature locally, and so if I want the battery pack to age in a uniform way, all of the cells should have very similar temperatures. If some cells turn out to age more quickly than others, then some will become weaker than the others. And as usually, the weakest cell in the battery pack that limits performance rather than, for example, the average cell in a battery pack. So even if all of your cells are in fantastic health except for one, that one weak cell will limit what your battery pack is able to do. Keeping cells at uniform temperatures also helps to maintain consistency. Two different methods are commonly used to cool a battery pack. One is forced air cooling, where fans can direct air across the battery cells in order to cool them. And the other is liquid cooling, where some thermally conductive liquid is run through pipes or plates, right up next to the cells to remove heat from them. If the battery pack is used at relatively low rates, then air cooling may be sufficient. But if the battery pack routinely sees high power demand, then it will need a more aggressive cooling strategy to remove this heat because the heat is generated at a faster rate. It might not seem intuitive, but electric vehicles generally need less cooling per cell than hybrid electric vehicles. And this is because electric vehicles are designed for energy applications, for long-range applications, so each cell is discharged at a relatively low rate. And therefore generates heat at a relatively low rate as well, per cell. Hybrid electric vehicles have essentially zero electric range, and they're designed only to provide the peak power demand. And so power is drawn from cells at a relatively high rate per cell, generating heat at a faster rate as well. So again, that analysis is per cell, so you have to do the math to come up with the aggregate heat generation to see whether liquid cooling is required, or whether air cooling is sufficient. The two photographs on this slide show cutaways of two vehicles. The vehicle on the top is the extended range electric vehicle, the Chevy Volt, and the vehicle on the bottom is the Tesla Model S. Both of these vehicles use liquid thermal management. In the Chevy Volt, the battery pack sits between the driver's seat and the passenger seat in the front of the vehicle. And it runs down the center of the vehicle between the passenger seats in the rear. And then splits off and makes a T-shape, and is behind the passenger seats in the rear. And in this design there are plates inserted between cells in the battery pack. And these plates have thin, tiny channels in them through which the liquid is pumped to remove the heat generated by the cells. In the Tesla Model S, the battery pack is located in the floor underneath the entire passenger compartment, and liquid is passed in between the cells in this region to cool them. In some cases it may actually turn out to be advantageous to implement heating in addition to cooling. If we have the ability to heat a battery pack, then we can charge the pack, even if the ambient temperature is quite low. Because we can cause the temperature of the battery pack itself can be warm enough to charge without risk of lithium plating and damage, even though the outside temperature is cold. Notice that the biggest reason we might want to heat a battery pack is to enable charging. And so heating will be done probably only when the battery pack, the vehicle, is plugged into the utilities grid. And so we are not wasting battery pack energy to heat the battery pack. Instead we are using the utilities energy in order to heat the battery pack. Also, because of the resistance of the battery cells, as I am charging and discharging, even a cold battery pack tends to heat up fairly quickly. So this is why cooling is more important than heating, usually. In some cases we may also wish to cool the battery pack below ambient temperature. Air cooling and liquid cooling exchange heat with the environment and so are able to bring the battery pack temperature down no further than the ambient temperature. But instead, if we use some kind of a refrigerant in our cooling system, then it's possible to cool the battery pack below the temperature of the environment. This is going to require significant energy. And so it may not be a good idea when the vehicle is in operation because we are using the energy from the battery pack to do so. But if the vehicle is parked and the vehicle is plugged into the utilities grid, then it can be a good idea. Because it can bring the temperature of the battery cells down into a more healthy range and extend the life of the battery pack. In the United States, one of the cities that's often used as a benchmark is Phoenix, Arizona. If you've been there in the summer, you understand why. Phoenix has very elevated temperatures in the summer. And a vehicle not operating, simply parked on the pavement, encounters really extreme temperatures, even up to 50 or 60 degrees Celsius just parked. And so I think you can see why the ability to refrigerate the battery pack when the vehicle is stationary might be a good thing to do in that situation. So to summarize this very short section, you've learned that it's important to keep the battery cells in a comfortable temperature range to ensure safety and to extend the battery pack's life. It's also important to keep the cells at a uniform temperature so that they will age at a consistent rate. And this has the side benefit of reducing the need for many temperature sensors, since we can quite safely assume that the temperatures of most cells are relatively the same. In present commercial automotive battery packs, we either have air cooling or liquid cooling. There are some reports that range and life are negatively impacted by air-cooled systems, since the air cooling is not as effective as liquid cooling. Liquid cooling systems are more expensive, but they're able to extract more heat at a faster rate than air-cooled systems are able to do. Active heating and active cooling while the vehicle's plugged into the utilities grid can extend life and can also shorten charge times, especially if the ambient temperature is cold. By bringing the temperature of the battery pack into a range that will enable faster charging. And finally, I remind you that the focus of this specialization really has to do with designing algorithms for battery management systems. The focus is not on the thermal management system of the vehicle. And in fact, the thermal management system is an enormous design challenge. And you could probably have an entire specialization simply on that topic. But I'll leave that up to someone else to develop, who's an expert in that area. So that brings us to an end of this section, and an end to the major topic areas of this week. The remaining section is a summary section that looks at what you've learned, and looks ahead to the topics that we are going to look.
A battery management system must provide monitoring and control to protect in two different ways. The first one that we'll look at is the requirement to protect the battery pack cells from out of tolerance ambient conditions. The second is to protect the users from the consequence of battery pack failures. And as you have already learned, high energy storage batteries can be very dangerous. If energy is released in some uncontrolled way, this can have catastrophic consequences. One example is if there is a short circuit inside one or more of the battery cells, that will cause large levels of electrical current to flow, which will cause a lot of heat to be generated, which will cause thermal runaway and fire in the battery pack. A second example is if there is physical damage to the battery pack, such as if a vehicle is involved in an accident, and this can lead to very unpredictable energy release due to crushing or penetration of the cells and so forth. If a battery cell develops an internal or external short circuit, hundreds or even thousands of amperes can develop in microseconds. So if you want to have any hope of protecting against a short circuit, the protection circuitry must act extremely quickly. This is very difficult, and in many instances, the best we can really hope to do is to isolate the damage caused by the short circuit in one cell so that it does not propagate to the other cells in the battery pack. Different applications and different cell chemistry require different degrees of protection. A failure in a lithium-ion cell can be very dangerous, and it can lead to a fire and even lead to an explosion. In many applications, including in the automotive environment, protection is indispensable. When we are designing protection for a battery pack, we must address the following undesirable events or conditions. We must address excessive current during charging or discharging. We must address the possibility of and response to a short circuit. We must consider over voltage and under voltage. We must think about high ambient temperatures and overheating of the battery pack. And we need to look at what happens if isolation is lost. In other words, if there is a ground fault. And we also need to think about what to do if there is abuse to the battery pack. When we are designing protections, we should also consider what happens if our protection mechanism itself fails. Whenever possible, we should implement reductant protection paths so that if the primary protection mechanism fails, then the secondary protection mechanism will still be able to protect the user and the battery pack. The drawing shows a graphical way the region of operation in which we would like to operate our battery pack and the region that we would really like to stay away from. In this case, the horizontal axis is temperature and the vertical axis is magnitude of electric current. The region that is shaded in red indicates location where it is unsafe to operate the battery pack in terms of temperature and current magnitude. Any point that is not color red is technically an acceptable point at which we can operate the battery pack. However, we would like to leave a safety margin in our design so that we not only stay out of the red zone, but we also don't even really get close to the red zone. So we define this green region that you see, which is what we call the safe operating zone, that is separated from the failure zone by a safety margin region, which is shaded in white. We choose our safety devices to constrain operation to be inside of the green region. For example, our design might include a thermal fuse. Whenever the temperature increases beyond the fuse set point temperature, the fuse will trigger and operation will cease. The operation boundary of the thermal fuse is drawn as a vertical line on this diagram. To the left of this line, the fuse is not activated and operation continues as normal. To the right of this line, the fuse has activated and has shut down the battery pack. We might also consider using a resettable fuse. A resettable fuse is characterized by the diagonal line, and that's a function of both current and temperature. So whenever current goes above a certain level at the present temperature, or whenever temperature goes above a certain level at a certain magnitude of current, the resettable fuse will trip, and again operation will cease until the temperature goes down enough that fuse resets. We can also consider some kind of an electric protection that is also monitoring the magnitude of the electrical current and will again discontinue operation when the circuit determines that electrical current has gone above some magnitude. So what's important in this diagram is that you notice in order to go from the safe operating zone shaded in green color to the unsafe failure zone shaded in red, a minimum of 2 of these protection mechanisms must be bridged to do so. This means that to enter the failure zone, at least 2 of the protection system will have failed completely, or to put in another way, we are almost certain that we will never enter a failure zone because we have at least 2 protection mechanisms that will always keep us from doing so. Again, if one of our safety mechanism fails, we will enter the white region, which is a safety margin, and it's still safe to operate in that region. It's only if 2 of our safety mechanism fails, then we will enter the failure zone. We can draw a similar diagram when we consider protecting against over voltage and over temperature together. The diagram illustrates the temperature, once again on the horizontal axis, but this time with voltage on the vertical axis. The thermal fuse can protect against over temperature. Different kinds of electronic protection can protect against over voltage and under voltage. For example, when we consider over voltage, our battery management system might have dedicated electronics that monitor the voltage of individual battery cells and shutdowns. Or the software in our battery management system might additionally monitor these voltages and shut down when they become too high. Additionally, when we think about over voltage, the most likely case leading to the over voltage is when we are charging the battery pack, when we are plugged into a charger. So the charging system might have its own over voltage circuitry or software detection mechanism that can notice if there is a problem and respond to it. On the under voltage side, our battery management system can once again have either electronic or software based under voltage detection, and the load connected to the battery pack can also implement under voltage protection mechanism. We do need to be a little bit careful when adding this protection mechanism, however, especially if they are electronic mechanism, because each of the devices that we add into the main current carrying path will add some kind of resistance to that path, and that will reduce the power that's delivered to the load and also increase the amount of heat that's generated in the battery pack. It will also increase the cost of the battery pack because of the additional components that we are adding. So we don't want to add an enormous number of these protection devices. But we do want to be careful in our design to add a sufficient number to meet safety standards. Some examples to be considered when designing safety mechanisms include a thermal fuse that operates when the present temperature is above some limiting temperature, a conventional fuse which is designed to prevent overcurrent but also operates based on an internal temperature. A note, however, on the conventional fuse is that it operates when it heats up internally and an internal element vaporizes basically, and this may not act quickly enough to protect against some very rapidly accelerating event such as the result of a short circuit. So we might need to consider more active fault detection, by which I mean an electronic device coupled with software instead of some passive device. In addition to protecting the battery pack from environmental conditions that compromises safety hazards, we also need to be able to build into our design the ability to detect operational faults and to be able to tolerate and whenever possible rectify these faults. For example, current state-of-art battery management system use processors that have dual processing cores. These cores execute the same instruction at slightly different time offsets and then compare the results of the instruction against each other. When the results don't match, these can trigger execution of additional code that tries to recover from that fault or at least to inform the users that something went wrong. In a master-slave battery management system, the slave system can also often detect self faults without any additional input processing by the master. For example, many of the battery management integrated circuits that we looked at previously can detect automatically over voltage or under voltage at a cell level based on thresholds that have been programmed into that slave by the master BMS. They can also often monitor for over temperature and under temperature since they are also measuring those quantities. And in some cases again, the slave integrated circuits themselves can be reductantly implemented so that you have two slave chips measuring the same physical quantities and comparing results against each other. But if those results do not agree, then at least one of the result is wrong, and that can be reported to the master BMS, which will take appropriate action to respond to that. If a slave determines that there has been a very serious fault, it may, in some cases, be given authority to shut down the battery pack without involving the master microprocessor. This is an extreme condition and not one to be undertaken very frequently, but it can help to save a battery pack and to ensure safety when communication with the master microprocessor has been lost or when the master microprocessor has failed entirely. So monitoring voltage faults and temperature faults is fairly simple, but there are some other types of faults that are much more complicated and must be detected using software. One example is the method that you learned for detecting isolation faults. All of this discussion also brings up the realization that the communication link between the master and the slave must have very high electrical noise immunity or very high EMI, that is electromagnetic interference immunity. We really desire that the communication be robust and reliable and fault free in order to have an overall robust battery management system that's able to detect the safety of the battery pack and to perform all of its normal required operations. Whenever we are designing a battery management system for a specific application, it's also important to be aware that there are different international safety standards that must be complied with. For example, when designing a battery management system for a passenger vehicle that has a maximum vehicle weight up to 3500 kilograms, we must comply with the ISO 26262 safety standards. If we are designing a battery management system for an electric motorcycle, we must comply with the ISO 19695, and this is similar to but somewhat different from the ISO 262. Or if we are designing a battery management system for trucks larger than 3500 kilograms, which includes even commonly seen vehicles like the Ford F250 or Chevy Silverado and others, then we must comply with the IEC 61508. Now, it's not the goal of this specialization to talk about safety standards. They are quite complicated and they would require courses of their own really to understand them and how to implement them. At this point, I simply want you to be aware that these standards exist, and it's important when designing a BMS, such that our software and hardware designs comply with these standards. The fact that there are different standards for different applications tends to make it difficult to have one universal BMS that can apply to any application at all. The safety standards I have listed all have the same general goals, but they are somewhat different in how they describe these goals and in how they apply them. For example, they define things called safety integration levels or SIL and evaluate them though in a different ways. So it's challenging to design to all of these standards simultaneously, and as I have mentioned, these standards are complicated and require courses or specializations of their own to understand them completely. When implementing BMS software, the amount of time and code required to satisfy the standards should also not be underestimated. Some of my colleagues that I have in the field tell me that 40% or more of the BMS code is written specifically to address safety standards. So to summarize this lesson, you have learned that it's critical to protect the battery pack operator and the battery pack itself. It's good design practice to require multiple protection to fail before the battery pack itself is able to fail. Along the same lines, it's important to have redundant sensing and processing to make a robust design to enable fault detection. And finally, there exist international standards that inform as to the best practice design that can lead to the robust and fault tolerant implementations. But these are beyond the scope of this specialization. So that concludes these lessons on safety and protection. And from here, we move on to look at the remaining BMS requirements. Till now, you have learned about the requirements 1 and 2 of a battery management system, which have to do with sensing and high voltage control and protection. In this lesson, we are going to consider requirement 3, which has to do with interface between the battery management system and the host application. This includes the communication itself, It also possibly includes controlling a charger, data recording for diagnosis purposes, and it can include auxiliary tasks such as range estimation. Let's first think about how the BMS communicates with the host application. There are many ways of doing this, but a very common approach that's used in a lot of applications is the Control Area Network or CAN bus, which is an industry standard way of communicating. In the automotive application, it's the universal way of communicating between the electronic components in the vehicle. The CAN bus specification is designed to provide robust communications between two processors in a very demanding and harsh automotive environment, where there are high levels of electrical noise. It's already used in conventional vehicles where these noises come from spark plugs firing, for example, and so it's a natural choice on moving to electric drivetrains where there's also a significant amount of electrical noise generated by the electronics that drive the power for the electrical motors. The CAN bus uses two wires and communicates in a serial fashion, one bit at a time between the two processors. It's designed to network intelligent sensors and actuators and processors together, and it's able to operate the two rates simultaneously. One of these rates we would consider a high speed rate. It might be around 1 million bits per second or roughly 1 billion baud. The high speed operation is used for critical things such as engine management and the vehicle stability and motion control, and things that are performance critical and safety critical. The low speed operation might work at 100,000 bits per second or roughly 100,000 bauds. The low speed CAN bus might be used for simple switching control of light, operation of power windows and mirror adjustment, and the instrument display and other functions where the safety performance are not as time critical. The CAN bus protocol defines how to transmit information between two different entities connected on the bus in the following way. It gives a method to address the messages to a specific destination device connected to the bus. It defines the data format to be used in the message. It defines the transmission spread of the high speed and the low speed aspect of the protocol. It also defines priority setting for a message being transmitted on the bus, and it defines sequencing of messages and responses. It also talks about how to detect errors and how to handle those in order to get retransmissions, so that we are able to communicate everything that we desire to communicate, and it defines some control signals. I have illustrated the format of one frame of canvas message here. The frame begins with a single bit. That's a start of frame or SOF maker. Then this is 29-bit identifier for the address of the recipient of the message. Then there is 1 bit ready to receive or RTR field, and this is followed by a 6-bit control field that describes what this message is all about. The main part of the message is a data field with the information that has to be transmitted across the wire, across the bus from the transmitter to the intended recipient. Then this data field can have a length of anywhere between 0 and 8 bits. This is followed by the checksum that's used to detect whether there have been any transmission error in the message, and this checksum is often called a cyclic redundancy check or CRC check. The next field is a 2-bit acknowledgement field that's used to acknowledge correct receipt of a message. And finally, the message concludes with a 7-bit end of frame or EOF. which when combined with the 1 bit start of frame puts bookends on the message so that the recipient knows that the entire message has been received correctly. These data frames are transmitted sequentially over a bus that's shared between many devices. When data frames are successfully received, an acknowledgement is sent back. If a data frame is not received at all, there will be no acknowledgement, and so after some time out period, it's retransmitted. If the data frame has been received correctly, then the acknowledgement will be sent back to the original sender, and so the sender knows there's no need to retransmit. One application that requires the battery pack to communicate with the outside world is when the battery pack is being charged. Battery packs are charged generally in two different ways. One way is what I will call random charging. This is when charge is delivered in unpredictable patterns to the battery pack from the host application. In a vehicle, this happens when the driver presses the brake pedal, and instead of using the friction brakes, it's possible to use the motor to put the braking energy through the motor back into the battery pack to add charge to the battery pack. And this recovers some of the energy that would otherwise be lost and improves the efficiency of the vehicle. Now, of course, in a vehicle, you still need the reductant friction brakes, and so regenerative braking is used for only a portion of the overall braking need. But it does help to increase efficiency. Control of random charging is done by providing the host application with charge power limits that must be obeyed at all points in time, and these power limits are dynamic in sense that they change as the state and the environment of the battery pack changes. And so the battery management system must continually calculate how much recharge power the pack can safely accept and then transmit this limit to the host application. The second type of charging is what I will call plug-in charging, and this is used in an electric vehicle that can be connected to the electric power grid. So this concludes pure electric vehicles, of course, and plug-in hybrid electric vehicles and extended range electric vehicles. In this application, it's possible to communicate directly from the battery pack through the host application to the charger to control the charger's output, current and power directly. So the battery management system can then ensure that the voltage of the charger meets certain requirements, and it can conduct balancing of the different battery cells and of the battery pack while charging is happening. The motive of plug-in charging often follows what we call a constant power, constant voltage mode, which we saw earlier in the course. There are more exotic methods that are possible, and it's my belief that future electric vehicle charging will be optimized in order to charge the battery pack quickly and safely, and that this optimization process will turn out to be somewhat different from standard constant power, constant voltage charging. Lithium-ion cells can safely accept much faster charging when they are warm than when they are cold, and so some battery management system implement heating that activates the vehicle is being charged when it's plugged in. The heating system is powered directly from the grid, and so battery energy is not wasted in order to activate these heaters. And so the heating system makes the battery pack last longer in the sense that it can charge more quickly without causing damage, which is a huge advantage. We were talking about charging. I would like to perform a really fun thought experiment with you. One of the things that's limiting consumer acceptance of electric vehicle is the rate at which they can be recharged. So we might want to consider what limits that rate. Let's think about this. First, we need to think about how much energy is required when we are charging the battery pack. And it turns out that most passenger vehicles of moderate size require between 200 to 300 watt hours per mile traveled. And this is a value that we can verify later in this specialization. So if we desire a 300 mile range, the battery pack must have been 60 to 90 kilowatt hours of capacity. If we are to charge the entire battery pack in 3 minutes, which is roughly the time it takes to refill a gasoline tank of a standard automobile, then it would require a power transfer at that rate of about 1.8 megawatts, and that's an enormous amount of power. So instead of thinking about what's required to charge in 3 minutes, let's think from the other point of view of how much power is commonly available. In the United States and a household standard circuit, electrical power is provided at 110 volts AC and 15 amperes, and this is roughly 1.5 kilowatt. And charging at this rate is termed level 1 charging. Level 1 circuit that is able to recharge the battery pack is about 40 to 60 hours, and clearly that's far too long. So we must consider other levels of power that might be available. Again, in the United States, it's also quite common for households to have specialty circuits for the electric stoves, for electric clothes dryer that operate at 220 volts AC and between 30 to 40 amperes. This corresponds to about 6.6 kilowatts, and this type of charging is called level 2 charging. Level 2 charging is able to recharge a battery pack of this size in between 10 to 15 hours. So that's still very long, but clearly it's far better than level 1 charging. And in fact, since most people don't drive 300 miles every day, level 2 charging is generally considered sufficient for most vehicle applications, unless you happen to be driving very long distances between two destinations. And so there is something called level 3 charging, which presently exists in multiple forms. One uses direct current and operates up to a limit of around 500 volts and about 125 amperes. This can charge a battery pack up to about 80% state of charge in about 30 minutes. Tesla has implemented their own proprietary level 3 fast charging system for their Model S, and that can provide about 50% state of charge in about 20 minutes. So you see that in most cases, the limit to how quickly we charge battery pack is not truly the battery chemistry. Instead, it's the electrical service to which the battery pack is connected. But it's also true that the battery can limit charge rates, especially at low temperatures and at high state of charge. So present research on fast charging is concentrating on how can we accelerate that final 20% of charge and how we can safely charge a battery pack at low temperatures. A third function that I associate with the communication requirement of the battery management system is that of maintaining a logbook. For warranty and for diagnosis purpose, the battery management system should store a permanent record of unusual or abuse events. This record should include a description of what the abuse was, such as whether it was a measurement that was out of tolerance or whether there was some over voltage or under voltage or whatever, too much current was measured or something like that. It should also measure the duration of the abuse event and the magnitude of the abuse event. Since an over voltage event of 1 microsecond is probably not that a major concern, but an over voltage of 1 minute could quite easily be a significant concern. This logbook can also store diagnostic information that is not directly related to any unusual event, but it could be useful in determining how this battery pack has been used over a long time. It can store the number of charge and discharge cycles completed. It can store the state of health, estimates at the beginning or ending of every tricycle, and it could store just about anything you can think of that should be maintained between one point in time and another point in time, such as when the battery pack is removed from the load and when it's reconnected to the load. This record is stored in non-volatile memory, for example flash memory, such as used in solid state drives in your laptop or on a USB thumb drive. This data can be transmitted to the host application when required. But many battery management systems have secondary diagnostic interface so that a technician is able to access the data directly without requiring a path through the host application to do so. This way, the technician can determine directly from the battery management system the information that's required to diagnose a problem and which can lead to some ability to correct the problem. There are other tasks battery management system might do in cooperation of the host application. This would tend to be more application specific, and the one that I talk about here briefly applies to electric vehicles. In that case, the host application might require the battery management system to compute an estimate of the present remaining range of the vehicle based on the amount of energy remaining in the battery pack. This, however, turns out to be a quantity that heavily influenced by environmental factors such as what are the vehicle characteristics and how is the vehicle being driven and what is the surrounding terrain, such as are there many hills, will I be going up or down a lot, what is the weather like, is there a lot of snow on the ground that's causing friction, or is there a lot of that's either impeding or helping progress. It even matters whether the ambient temperature is warm or cold and how the vehicle will operate. So range estimation is very difficult. It depends not only on how much energy is available on the battery, but also on the characteristic data truly known only by the host application. And so, at this point in history, it appears to me at least that every automotive manufacturer will have their own range estimation algorithms. But again, later in the specialization, towards the end, we will see how to simulate an electric vehicle, as an example battery load, and you will be able to see perhaps how range estimation might be done. At this point, it's sufficient to know that battery management system must at least produce the inputs to these algorithms, and especially for the range estimation algorithm, how much energy is presently available in the battery pack. To summarize this section, you have learned that a battery management system must communicate critical information about the present operating condition of the battery pack to the host application. This is very often done using a CAN bus protocol, and since CAN bus electronics are implemented in hardware already on many microcontrollers that are available off the shelf, this is not a difficult thing to do. The communication needs and requirements tend to be application specific, but there are some common features. The battery management system must often give information about how to control the battery pack charging system in order to avoid safety hazards. The battery management system must often maintain a logbook of unusual or abusive events. The battery management system may also be required to perform application-specific tasks that might include computing an estimate of how much available range is left or distance to empty estimate for an electric vehicle. And of course, the battery management system must communicate to the host application estimates of available energy and available power and state of charge and state of failure and so forth. And so we will begin to consider the estimates that a battery management system must provide to the host application. Last section, you learned that there are 5 major requirement areas that must be satisfied by a battery management system. So far, you have learned about requirements 1 to 3 in more detail. In this lesson, we consider requirement 4, which has to do with the performance management, and this includes computing estimates of state of charge and available power, and having an ability to balance or equalize cells in a battery pack. Fundamentally, application using battery packs need to know 2 basic quantities that describe the present state of the battery. And the first is how much energy is available in the battery pack. The second is how much power is available in the immediate future. And this I tried to illustrate by drawing a glass of soda and a straw. And I will explain what I mean by this as I continue. Knowledge is about how much energy is available in a battery is most important for applications like electric vehicles. Energy tells me how much work I can do. In an electric vehicle, the energy estimate informs me as to how far I am able to drive before I must recharge the battery pack. In this illustration, we can compare the amount of energy in a battery to the amount of soda in a glass as an analogy. When a battery is fully charged, there's a lot of energy available, and when the battery is fully discharged, there is no energy available. It's the same with the glass. When the glass is full, there is a lot of soda in it. When the glass is empty, there is no soda in it. And energy is a total quantity talking about a total amount of work that we can do. We can contrast that with the concept of power. Power is the rate of energy usage, knowledge of how much power is available in the immediate future, which is the most important for applications like hybrid electric vehicles. This information tells me whether I can accept to recharge energy quickly or whether I can provide energy quickly to accelerate. In the example, power is illustrated by the straw. If the straw has a wide diameter, then we can extract soda quickly from the glass. If the straw has a narrow diameter, we can extract soda only slowly. So energy and power are like soda and a straw. If power and energy estimates are important for applications like extended range electric vehicles and plug-in hybrid electric vehicles, because they need to know how far they can drive, but they also need to know how quickly they can accelerate and decelerate. It turns out that no sensor exists that's able to measure the available power or available energy. Instead, we can create methods to estimate the amount of energy and power. And in order to estimate energy, we must know at least all of the cell state of charge and all of the total capacities of the cells in the battery pack. To estimate power, we must know at least all the cells state of charge and all of the resistance of the cell in the battery pack. No sensor exists that can measure state of charge or capacity or resistance directly. So we must find ways to estimate these values, and the diagram here shows the overall process. To the right of the diagram, we see the desired output of how much energy and how much power might be available from the battery pack. In order to come up with these estimates, we need to know all of the capacities of the cells, denoted as Q. And we must know all of the states of charge of all of the cells, and we must know all of the resistance of all the cells, denoted by R. Once we have these values, we can perform deterministic calculations to arrive at how much energy and how much power are available. But we can't measure state of charge or capacity or resistance directly. So we must somehow come up with values for these quantities using things that we can measure. The available input includes cell voltage and battery pack current and either cell or module temperatures. So we use those basic measurements with computer method called algorithms to come up with estimates of capacity in state of charge and resistance. And those estimates then feed the power calculations, and in the end we are able to compute the estimates of energy and power that we require. It turns out that there are both good methods and poor methods to produce estimates. There is not only one way to do it. The simplest methods are usually, unfortunately, the least effective methods also. And there is some impact to implementing a poor estimator. One of these could be an abrupt correction when a voltage or a current limit is exceeded. For example, if a battery management system in a vehicle tells the vehicle control computer that 50 kW of power is available, and then that vehicle draws that power to start accelerating. But then the battery management system says, sorry, I was wrong, that's too much power. My cell voltage are now too low. So what's going to happen? One thing could be that the battery management system or the vehicle control computer decides to simply cut off power to the vehicle in order to protect the battery pack. But that would be an enormous safety concern, and the customer furthermore will develop some perception that the vehicle exhibits poor drivability and will be very unlikely to purchase your product again in the future or to recommend it to someone else. Another alternative, when a bad estimate has been made and the battery management system says, no, the voltages are too low, is to just accept that condition and keep on operating. Even though it's causing some damage, the cell will still allow the vehicle to use energy from the battery pack in order to accelerate, because I promise the vehicle that was able to do so. This might be last in immediate safety concern, but it does cause damage to the cell, which is undesirable consequence. So the most common approach to compensate for uncertainty introduced by poor battery management estimation algorithm is to over-design the battery pack by putting in too much capacity for the application, and then by derating the estimates of energy and power that we tell the host application in order to ensure that we never overcharge or over-discharge the battery cells. So as an example, if I calculate that there is 50 kW of power available, but I don't trust my estimate, I might multiply that value by a factor like 0.8 and then tell the vehicle that there is only 40 kilowatts of power available. So clearly we are not using the entire capacity of the battery pack if I do that very often. So all of these responses to using a poor estimation algorithm had cost in dollars or euros or whatever currency, and cost also in a weight and volume if I need to add more battery cells that are really required by the application. So we would rather prefer to do a better job of creating estimates, and you might wonder why there is a picture of this gentleman here. His name is Rudy Kelvin, and he was the inventor of a technology known as the Kelvin filter. Kelvin filters turn out to be the optimal way of estimating the internal state of some dynamic system when we have the ability to measure only the inputs and the outputs of that system. Later in the specialization, we are going to spend a lot of time investigating this method called common filtering, and you are going to learn all about it, and you are going to learn how to implement the Kelvin filter and some of its variation that work for non-linear systems such as battery cells. and you will learn how to apply the extended Kelvin filter and the sigma point Kelvin filter of uncentered Kelvin filter to estimate battery cell state of charge. And when we get depth into the course, which takes a few weeks to learn how to do this, but the outcome will be that you will know how to perform state estimation so much better than can be done using some of these poor methods, and you learn how to find the near optimal solution for estimating state of charge of battery cells. So to summarize this section, you have been reminded that applications need to know at least two principal quantities about the battery pack: how much energy is available and how much power is available in the near future. Unfortunately, we are not able to measure these quantities directly, and so we must estimate them based on knowledge of state of charge and capacities and resistance of cell in the battery pack. Again, these quantities also are not things that we can measure directly, and so we must estimate their values using measured quantities like cell voltage and battery pack current and temperatures. The major premise of this entire specialization is that investing some time learning about good battery management system algorithms, and by investing some money on good battery management system electronics and algorithms can ultimately lead to reduced battery pack size and result in considerable cost saving when building a battery management system and selling many quantities of it. So later you will learn how to create mathematical descriptions or model of battery cells that are needed by these algorithms. Also, you will learn about advanced methods of state of charge estimation including Kelvin filtering and state of health estimation, which will allow you to compute estimates of battery cell capacity and resistance. And lastly, you will learn about how to balance a battery pack and how to estimate power limits. Over the remainder of this section, we will talk about a preview of some of these. We can't go into depth until we do it in the sequence, but you will at least see ideas of the concept involved that you will learn over the rest of the specialization. In this section, we continue to explore requirement 3 of the battery management system, which has to do with performance management. We are thinking specifically about the requirement for state of charge estimation, and it's worthwhile to think a little bit about what truly does state of charge mean. You have probably already have a good initiative into tube filling for the state of charge based simply on using electronic devices that have state of charge meters. These might include the state of charge indicator on your notebook computer or on your mobile phone or on some electronic devices. So you already understand when the meter reads 100%, that battery is fully charged, and when the meter reads 0%, the battery is empty. But is this display something that is empirical and not truly physical, or does it correspond to something that is truly physical, even though it may not be measurable directly? The diagram here shows a schematic of lithium-ion battery cells, where we are thinking about how lithium moves inside the cell as the cell is operated. When we discharge the cell, lithium moves from negative electrode across the positive electrode, and when we charge the cell, the opposite happens. Lithium moves from positive electrode over to the negative electrode. So if you think about it, when the cell is fully charged, there will be a lot of lithium in the negative electrode, and when the cell is discharged, there will be much less lithium in the negative electrode. So thinking about it that way, we can connect our intuitive ideas as state of charge directly to the physical quantity of how much lithium is present in the negative electrode particles, or equivalently, what is the concentration of lithium in the negative electrode particles of the battery cell. In this specialization, we do not spend very much time talking about modeling or understanding lithium-ion battery cells at electrochemical level. For this specialization, it's sufficient to have a simple understanding of this one concept that we talk about here. You already learned that lithium can be absorbed into negative electrode. You might know that lithium can be absorbed into negative electrode particles by entering into the empty spaces of their crystal structure. There are some maximum amount to how much lithium can possibly enter into those spaces before it's completely full, and we call this concentration CS max. C for concentration, S for the solid particles of the electrode, and max, of course, for the maximum value. So when the particle is completely full of lithium, the concentration of lithium in the particle will be CS max. And similarly, when the particle is completely empty of lithium, the concentration will be 0. At any other intermediate point, we have some other concentration. And when considering cell state of charge, the important quantity is not the local concentration at any point in the electrode, or even at any point in a particle in the electrode, but instead it's actually the average concentration over the entire electrode, which I am calling CS average, perhaps at time k. So we can normalize this present average concentration by dividing it by the maximum possible concentration to give us a value that's always between 0 and 1, and this value is called the stoichiometry of the electrode, and it's often denoted by the symbol theta, and here also with the subscript k, which refers to a point in time indexed by k. The stoichiometry is a number, as I said, between 0 and 1, and we can consider it to be a kind of an electrode state of charge. But we must understand that this electrode state of charge is different from what is reported to the user as a cell state of charge. You might remember that in some electrodes we are not permitted to charge above a certain concentration or discharge below a certain concentration. So the stoichiometry is not permitted to use the entire possible range between 0 and 1. There is a lower limit to the stoichiometry before the cells begins to deteriorate quickly or is unable to provide adequate power. Similarly with the upper limit, and so this cell is always operated above the stoichiometry of 0. So when a cell is at 0% state of charge over for the whole cell, the stoichiometry for the electrode, which we call theta, 0% is actually a number bigger than 0. And correspondingly, when a cell is at 100% state of charge, the stoichiometry or the electron state of charge is at some value less than 1, that we call theta 100%. So we are going to operate the cell between a stoichiometry of 0 and 1, but rather than between stoichiometry of theta 0% and theta 100%. In other words, when the cell is at a stoichiometry of theta 0%, it actually has a cell level state of charge of 0%, even though the electrode state of charge is above 0. And when the cell stoichiometry is at theta 100%, the cell state of charge is at 100%, even though the electrode state of charge or stoichiometry is less than 1. So this might actually give you some insight into how it's possible to overcharge a battery cell, or how it's possible to undercharge a battery cell. It's physically possible to remove more lithium than theta 0% to get all the way down, at least in principle, to 0. And it's possible the charge above theta 100% theoretically up till you get up to 1. But we don't operate out of this region. At least we intend not to operate outside of those regions for our safety purposes and for cell longevity purposes. So keeping the discussion in mind of what we have said so far, we can write the cell state of charge as equal to the present stoichiometry of the negative electrode minus the 0% value of that stoichiometry, all divided by the range between the 100% and 0% stoichiometries. And this relationship, while we have discussed it through the negative electrode, actually holds to the positive electrode as well as indicated by the second equation. The cell state of charge is also equal to the stoichiometry of the positive electrode minus its 0% value, all divided by the range between the 0 and 100% values. The tricky bit which comes in when we are using positive electrode numbers is that the numerator and denominator of this equation will both be negative. Well, it still results in a positive state of charge, but it's thinking about a little bit differently. The state of charge of a cell is actually a physical quantity. It's related to the average concentration of lithium in the entire negative electrode. It's also related to the average lithium concentration in the entire positive electrode. So if we were able to create a sensor that would measure this average concentration directly, then we could measure state of charge directly. But at least at this point in history, no such sensor exists. So it's natural to ask whether the concentration of lithium in the negative electrode is somehow directly related to things that we can measure, such as voltage. Well, it turns out that cell voltage depends on concentration of lithium at the surface of particles in the electrode, and in particular at the surface of the particles that are in direct contact with the negative current collector. Remember that lithium, as it diffuses into and out of the particles in the electrode, causes transient concentration difference between the surface and the bulk interior concentration of the particle. And these concentrations become the same only after time has elapsed, when the cell has been allowed to rest in an open circuit condition. So remembering the state of charge depends on average concentration of lithium, that voltage depends on surface concentration at one point. We can say that there is not a direct relationship between state of charge and the voltage that we measure right now. The two things are not the same. So there is no immediate direct correspondence between cell voltage and cell state of charge. In fact, cell voltage can change for a number of reasons, even though the state of charge could be constant. For example, if we change the cell temperature, the cell voltage changes a little bit, but the state of charge does not change. If we have been using the cell and then allow it to rest, the voltage changes as it's resting, but the associate doesn't change. And also, due to a phenomenon called hysteresis, cell voltage also depends not only on what's happening presently, but on the recent history of how the cell has been used. And that can lead to different steady state values even at the same SOC. And you are going to learn more about all of this effect later in this specialization when we discuss modeling behavior of lithium-ion battery cells. So in summary, state of charge changes only when we change the average concentration inside of an electrode, and these concentrations change only due to passage of current through the cell, either charging or discharging the cell, or due to self-discharge in the cell. So voltage turn out actually to be very useful as indirect indicator of state of charge and is very useful in state of charge estimation, but it's not a good independent predictor of state of charge. That's it by itself. If state of charge changes only when current passes through the cell, either due to some external circuit we're drawing that current or forcing that current, or due to self-discharge. Why don't we simply use measurements of cell current to estimate the state of charge? There's a perfectly valid equation that relates state of charge to cell current. And if you look at it, it says that the present state of charge at time t is equal to some initial state of charge at time 0 minus the total net integrated amount of current that is passed through the cell weighted by the efficiency factor eta and divided by the total charge capacity of the cell. What this equation is doing is integrating or counting the net number of coulombs of charge that have entered the cell and relating that to some initial charge level to update the present charge level. In this equation, electrical current is considered to have a positive sign when the cell is being discharged and a negative sign when the cell is being charged. In the equation, also the parameter eta, the Greek variable eta, is equal to the Coulombic efficiency of the cell, which is usually approximately equal to 1, but is never greater than 1, and Q is the total capacity of the cell measured in ampere seconds or coulombs. This capacity, by the way, is a physical quantity. It measures the number of vacancies in the electrode structure, and that crystal structure that could hold lithium between the stoichiometry of 0% and 100%. So this is not a function of temperature or rate or any other such thing. It's different from a discharge capacity, which is what is commonly put on a datasheet for a battery cell. It's a total capacity, it's the total charge capacity, if you will, and not at discharge capacity, and we are going to look at that in more detail later. This equation, I have said, is not very good for estimating state of charge, and yet is actually an exact representation of state of charge of the battery cell. We do not run into some very serious problem if we try to use it as our only basis of estimating state of charge though. Methods that do this are called Coulomb counting, because we are counting or measuring the number of coulombs that go into and out of a battery cell. But Coulomb counting suffers very serious inaccuracies when we can't measure current perfectly, which is always the case, or when we don't know Coulombic efficiency perfectly, which is always the case, and when we don't have a perfect estimate of the total charge capacity, and when we don't know the initial state of charge at time 0. So for this reason, Coulomb counting should never be used in a battery management system as a primary state of charge estimation method. And we will learn that there are much better ways of estimating state of charge. So in this lesson, you have learned that cell state of charge is directly related to something that is truly physical in a battery cell. Oftentimes people talk about a battery pack state of charge and mean by that some quantity that relates collectively to many battery cells at the same time. So I would like us to think for a few minutes about what is the battery pack state of charge. Let's consider the example illustrated here by the 2-cell battery pack drawn. The drawing shows one battery cell that's fully charged and it's shaded green, and one battery cell that's empty and it's shaded red. And these cells are connected electrically in series. So the charge passing through one cell must also pass through the other cell. And when we compute a battery pack state of charge, what should the value be? Should we define, for example, the battery pack state of charge to be 0%, because we recognize that this configure is not able to discharge. Notice that if we were to try to discharge, the current would flow out of this battery pack, and that would deplete the level of charge in the green cell, which would be fine. But it would also attempt to deplete the amount of charge in the red cell, which we would not, or at least should not do, because the state of charge of that cell is already 0. So we should not really define a battery pack state of charge to be 0%, because that implies that we are able to charge the battery pack, and we can't do that either. If we were to charge the battery pack, we would increase the level of charge in both cells. And if we increase the level of charge in the red cell, that would be fine. But if we increase the level of charge in the green cell, it would cause an overcharge situation, which we don't want to happen. So defining a battery pack state of charge of 0% does not make sense in this example. So maybe we should define the battery pack state of charge to be 100% because it's not possible to charge. But that's a really good solution either, because that gives us the idea that the battery pack state of charge is 100%. So I should be able to discharge, and we already know that we cannot do that. So how about reporting a battery pack state of charge as the average of the cell state of charge, in other words 50%. But we really can't do that either, because that implies that we are able to both charge and discharge the battery pack, and we can't do either one. So I propose to you that the term battery pack state of charge is something that frankly does not make a sense. It is ill-defined, and in my opinion, it should be never used. One thing that this discussion points out is that the battery pack should never end up in the situation that I have drawn. It's a requirement that we perform cell balancing or cell equalization to avoid this situation. But if you don't balance a battery pack, it is actually physically possible for a pack to arrive in the state of charge configuration drawn here. And if we even get close to this level of imbalance, we can see that the term or the concept of battery pack state of charge does not make sense. But people try to use it, and we might want to think about why someone would even care to know about that a battery pack state of charge is. One reason is for set point control. For example, in hybrid electric vehicle, we want to keep the state of charge of all the cells around or close to some set points, so that we can guarantee that there will always be some margin for charging and some margin for discharging the cells in the pack. For that application, knowing the average state of charge of all the cells in the battery pack might work as a set-off point, as long as none of the cells are at some extreme points. That is, a battery pack state of charge is not needed to perform set point control instead. Battery pack average state of charge is needed. Adding that one term, average, there clarifies exactly what we mean and makes it a lot more precise. Another application for which we might want to know a battery state of charge is at a distance to empty kind of calculation or a fuel gauge kind of calculation. But the true issue is not the state of charge of a battery pack, which I again argue does not make sense, but instead how much energy remains in the battery pack that might be used, and this is not the same thing as state of charge. So in my mind, there is no true application that demands knowledge of battery pack state of charge, and so my recommendation is that we don't even attempt to create an artificial quantity or another quantity by substitute battery instead. To summarize this section, you have seen that a battery cell state of charge has a real physical basis that can be connected directly to something happening internal to the cell inside of its fundamental electrochemistry. If we somehow knew exactly the average lithium concentration in either the negative or the positive electrodes, then we would compute the present stoichiometry of electrode, and we can compute the cell state of charge given the equation that we have already seen. Generally, we do not know this concentration, and so we ask whether direct measurement of voltage or electrical current can be used to tell us what is state of charge. And we have seen that it is not possible to use only voltage or only current to tell us what state of charge is. Somehow, we must combine this measurement in an intelligent way and use them to help us to estimate state of charge, and we will learn how to do this later in the specialization. Finally, battery pack state of charge is a concept that truly doesn't make sense, and I recommend that it not be used. Usually what people mean when they are talking about a battery pack state of charge is some kind of average of the state of charge of all the cells in the battery pack. If that's what's truly meant, we should refer to that as a battery pack average state of charge. And there are some real examples, real application where better battery pack average state of charge is meaningful and useful quantity, and we will see some of these later. In the meantime, though we are not going to think only about the cell state of charge, and that brings us to the end of this section, but we are going to proceed in the upcoming section to think a little bit more about the performance management. Two of the estimates that must be produced by the battery management system are the amounts of energy presently stored in the battery pack and the amount of power available over the near-term future. We are going to start our analysis of these requirements by first considering how much energy is available in a single cell in a battery. Remember that energy is an ability to do work, which can be measured either in watt-hours or kilowatt-hours. We can compute the total energy in a cell in a fairly simple way. The energy is equal to the total charge capacity of this cell Q multiplied by the area under the open circuit voltage relationship between the present state of charge and the minimum state of charge permitted by the application. This integral might look difficult to compute, but in fact it's possible to pre-compute its values and store them in a table for easy lookup. Using a table lookup interpolation scheme as the battery management system operates, which we will learn how to do in later video this section. So the total energy available in a cell has something to do with the voltage relationship between a minimum state of charge and the present state of charge and the total capacity. And this is sometimes adequately approximated by taking the nominal capacity and multiplying by the nominal voltage and multiplying that by the difference of state of charge between the present operating point and the minimum permitted state of charge. The figure on the left shows some example open circuit voltage relationship for 6 different varieties of lithium-ion battery cells that are tested and calibrated in the laboratory. The lower two curves correspond to 2 different varieties of lithium iron phosphate battery cells, and you can see that these have the characteristic of a very flat open circuit voltage relationship between about 10% and 90% state of charge. So the true open circuit voltage is actually very well approximated by the nominal voltage in the range, and this approximate relationship would very likely work quite well for iron phosphate type cells. The other 4 curves are for different varieties of lithium ion cells that include lithium manganese oxide and lithium cobalt oxide and manganese cobalt oxide cells. These voltage relationships are not quite as flat, and so the approximate energy computation would not be as adequate in this case or as accurate. But still, for some applications it might be sufficient depending on the nature of the application. Notice that the equation for energy is not a function of the magnitude of current used to withdraw that energy. In other words, it's not a function of the rate. To the first order, it's also not a function of temperature. We have already noticed that the total charge capacity of a battery cell is not a function of temperature, and while the open circuit voltage relationship has slight temperature dependence, it's not enough to change the available energy significantly. This statement might contradict your intuitive feeling for how much energy is present. If you have experienced working with lithium-ion battery cells, you might already know that it's impossible to get as much energy out of a cold battery cell as it is to get out of a warm battery cell, even if both were to start with the same amount to charge in them. But we need to be careful with what we are defining to the energy content in a cell. If a cell has 1 unit of energy, it does not depend if the cell is warm or cold, or how quickly we take the energy out of the cell. If I warm up the cell, that doesn't appreciably change the energy, except maybe for some thermal vibrations and some electrical chemical bonds, where that changes just a little bit. The amount of energy changes only slightly due to the difference in open circuit voltage in the cell. But if I try to extract this 1 unit of energy from a warm cell, I may be able to do so. And if I try to extract it from a cold cell, I may not be able to do so before encountering a lower voltage limit. And that's the key in countering the lower voltage limit. This is because the cell resistance increases at cold temperatures, and when we are discharging, we encounter this voltage limit more quickly because of the ohmic voltage drop of the cell. If I have a cold cell, maybe I can extract only 0.5 units of energy from that cell. But then, if I warm up that cold cell, it turns out I can extract the remaining 0.5 units of energy. So the energy was still here, it just wasn't available at that point in time because of the high resistance of the cell. So this equation, you have to compute how much energy is physically present, but it does not tell you how to extract all of that energy. And that's why we need power estimates in addition to energy estimates, because the power estimates tells you how quickly we can extract energy at this point in time. The power limits state the maximum rate at which we are able to move energy into the battery cell or out of the battery cell without exceeding electronics design limits or some battery electric chemical design limits. If I attempt to discharge or charge a cell at too high a power level, I will accelerate the rate of degradation, and that will lead to a premature battery pack failure. So we have just reviewed energy, which is a total quantity that describes a total amount of work that can be done. Power instead is an instantaneous quantity that refers to the rate at which we can do work. Power is equal to voltage multiplied by current, and it's measured either in watts or in kilowatts. When we compute power limits, there is an immediate challenge. We understand that power is an instantaneous quantity. Power is what's happening right now, but the host application probably doesn't care what's happening right now. Instead, it wants to do some planning. It needs to know how much power will be available in the near future, not just what's happening right now. So when we compute the available power estimates, we are not computing how much power is being used at this moment, which we could do very simply as current times voltage, and we measure both of those. Instead, we are informing the host application how much power it may use as some constant level for some future time horizon, and we call this time horizon delta t. So at this point in time, we compute a value of how much power is available, and we pass that value to the host application. And we are saying to the host application, you may use a certain level of power for the next delta t seconds without causing any violation in electronics or chemical design limits. This time horizon delta t is often on the order of 10 or 20 seconds. The sample period of a battery management system is often 1 per second or even faster. And this power estimate is something that we update every sample. So I don't tell the host controller you may use this much power for the next 10 seconds and then wait 10 seconds before giving it another update and how much power is available. Instead, I say this is how much power is available for the next 10 seconds, and then maybe 1 second later I update that quantity with, and by the way, now this is how much power is available for the next 10 seconds, and that will be somewhat different number. And so we end up with what's called a moving window power limit estimate. I am computing from now to a future 10-second value, and then 1 second later I compute from that point to a future 10-second value, and I keep on doing that. And this allows the host application to adjust a little bit more smoothly to changes in the available power as the host application draws power, or instead sources power that will end up recharging the battery pack. And there are some good methods and some poor methods for computing power. I will share with you one simple method to compute available power that's actually quite commonly used, but it does have some limitations, and so later you will learn some better methods. The figure in the left illustrates the simple method which is sufficient for you to understand right now. This method is known as the hybrid pulse power characterization or HPPC method. Is based on performing a very simple test on a battery cell in the laboratory and measuring some quantities from that test that will later use to calculate power. So the figure shows a profile of cell voltage versus time. The cell is initially allowed to rest until it has reached equilibrium, and in this slide that equilibrium voltage is shown to be 3.8 volts. The cell is then subjected to a discharge pulse that has exactly the same length as the time horizon delta t required for the power calculation. Then we allow the cell to rest again until it reaches equilibrium or at least close to equilibrium, which I have abbreviated here to also by only 10 seconds. The cell is then subjected to a charge pulse for the exact duration required when computing charge power. Finally, the cell is permitted to rest because we have designed this test and because we have implemented this test. We know the exact charging current and discharging currents used to create these pulses, and we also, from the voltage profile, we can measure the maximum amount of voltage change due to the discharge pulse and the maximum amount of voltage change due to the charge pulse. The maximum voltage change to a discharge pulse is measured from the beginning of the discharge pulse just before the discharge pulse is applied when the cell is still in equilibrium to the end of the discharge pulse when the voltage is at its minimum, that is our delta V discharge. We do the same thing for the charge pulse. We measure the change in voltage due to the charge pulse from the equilibrium point just before we apply the pulse of current to the maximum voltage at the very end of the pulse of current, and that is our delta V charge. From these voltage changes we can compute a charging effective resistance and a discharging effective resistance over the time horizons delta t that are required by the power calculations. The effect of charging resistance is the absolute change in charging voltage divided by the charging current, and the effect of discharge resistance is equal to the absolute change in the discharging voltage divided by the discharging current. These resistance are tabulated as functions of initial state of charge and temperature. Notice that if you are familiar with battery models already, please notice that the resistance we are calculating here is not that instantaneous or ohmic resistance of the cell. Instead, it's an effective resistance over the entire interval of delta t seconds, and it includes both the ohmic effects and also the diffusion effects as the voltage changes due to the slow time constants of the electrochemical processes in the cell. Once we perform the laboratory test and have calculated resistance at different state of charge set points and different temperatures and have stored these values in a table, we can use them in real time to compute available power estimates. In particular, we will use a mathematical model of how a battery cell works in order to predict how much power is available. The HPPC method assumes this circuit model that is shown in the diagram. In this model, the cell terminal voltage is described as an open circuit voltage at the present state of charge, along with a voltage drop across the effective resistance of the cell. In other words, the terminal voltage is equal to the open circuit voltage minus current times resistance. We can perform some simple algebra to find the electrical current in this equation, and this results in the relationship that current is equal to open circuit voltage minus terminal voltage, and all divided by resistance. When we use the HPPC method to compute the amount of discharge power that's available, we assume that we are concerned only with keeping the cell terminal voltage between some V minimum and V maximum limits. And so far, the maximum discharge power this would be achieved if the terminal voltage were also equal to V minimum. So to compute discharge power, we replace R in the current equation with the discharge resistance we tabulated from our test. And we replace the terminal voltage with the value V minimum. Then the discharge power is equal to voltage multiplied by current, which is equal to V minimum multiplied by the quantity of open circuit voltage minus V minimum, all divided by the effective resistance of the cell. To compute the amount of charge power available, we repeat the entire procedure, but we use a different assumed terminal voltage and resistance. That is, we use the simplified cell model where current equals open circuit voltage minus terminal voltage, all divided by resistance. But to compute the charge power, we replace the resistance with the tabulated charge resistance, and we set the terminal voltage equal to the maximum permitted voltage. We compute charge power then as voltage multiplied by current, or as the maximum voltage multiplying the quantity of open circuit voltage minus the maximum voltage, all divided by the effective charge resistance. Notice that this quantity is negative, that is, open circuit voltage must be less than the maximum voltage. So if we are required to report charge power as a positive number, we simply take the absolute value of this equation by multiplying this result by -1. Also note that this method, the HPPC method in general, uses a very simplified cell model that does not include all of the effects occurring inside the cell. And furthermore, that when we computed the effective resistance from our cell test, we assume that the cell was initially at the rest before we begin the experiment. So these equations are not perfectly accurate in a dynamic scenario for their real battery cell, and it's a common practice to derate the estimates produced by this equation by multiplying the computed power value by some factor slightly less than 1. For example, if we compute an available discharge power of 1 kilowatt, we might multiply that by some factor like 0.9 and report that 900 watts is available instead. This gives us some safety margin, but it actually officially limits the performance of the battery pack because we have used a poor estimation method. If we were to use a battery estimation method, we might be able to actually extract the full performance of the battery pack. So to summarize this section, you have learned how to compute cell total energy and cell available power. Cell total energy is easily computed if we already know the cell state of charge, the total capacity, and the open circuit voltage relationship of the cell. Cell available power is estimated over a moving time horizon at this future window that allows the host application to know how much power is available in this near future time frame, so that it can do some planning of how to use that power and then use the battery cell without causing damage to the cell or to the electronics connected to the cell. You have also learned about the HPPC method, which is a simple way to characterize the cell and to estimate power. But we have also learned that HPPC method has some limitations. So the HPPC computations, if you choose to use them, should be derated in practice in order to ensure safe and robust operation of a battery pack. This concludes the section on computing energy and power for a single cell. In the next section, you will learn how to compute the energy and power for a multi-cell battery pack instead. In the previous section, you have learned how to compute individual cell available energy and available power. The available energy computation was quite straightforward, but the available power calculation required a little bit more development. In this section, you are going to learn instead how to compute battery pack available power and available energy. That is, you will learn how to compute these quantities for a battery pack that comprise many cells wired together. You are going to see that computing available power for the battery pack is quite straightforward after you have learned how to compute the power for a single cell. So computing available energy involves a bit more a thought process, but in the end it's still not very difficult. So let's begin. Let's begin by looking at how to compute battery pack available power. Remember from last section that the HPPC method to compute cell discharge power evaluated the expression that the discharge power is equal to the minimum permitted cell voltage multiplying the present open circuit voltage minus the minimum voltage, all divided by the effective discharge resistance. In this equation, I have slightly updated notation from what you saw in the last section by adding the subscript J, so that we can remember that this is now a multi-cell battery pack, and this is power is begin computed at cell level for the time being. For a certain cell indexed by J in this battery pack, so I have had to update the voltage and the current symbols by now denoting them as V sub J and I sub J, and also the state of charge by denoting it as Z sub J. When computing power in a series connected multi-cell battery pack, we still consider the limiting condition to be when any cell voltage encounters either the minimum cell voltage for discharge and the maximum cell voltage for charge. So for discharge, the value V minimum in the power equation does not change, but the allowed current can change because individual cells might have different limiting currents. And in a series connected battery pack, the same current flows through every cell, and so we cannot permit more discharge current to flow through the battery pack than can be permitted by the weakest cell, the one that can permit the minimum amount of discharge current. So when computing pack power, we sum the individual powers. So we add up the power that is delivered as voltage times current for each cell. When we recognize that the current is going to be the same for every cell, but must be the minimum for all of the currents that are permitted by the HPPC method for individual cells that we talked about last time. And so you can see in this equation here, the discharge power is the sum over all of the cells in series of the voltage of that cell which we are setting to be the V minimum, and the current for that cell which we are setting to be the minimum over all of the currents allowed for all of the cells of open circuit voltage minus V minimum divided by the discharge resistance of that cell. Using the same reasoning for computing charge power for the battery pack, we compute the charge power as the sum over all cells of the maximum permitted voltage multiplying the current for that cell. And since charge power is negative and charge current is negative, instead of taking the minimum to get the minimum absolute value, we actually have to take the maximum. The maximum of two negative numbers has the minimum negative value, which is why you see the max in this equation. And that's all there is for computing battery pack power using the HPPC method. Now we move on to look at how do we compute battery pack total energy. Remember that cell total energy is computed as the full charge capacity of the cell multiplying the open circuit voltage relationship integrated between the minimum permitted state of charge and present operating state of charge. Often we say this would be approximately simply as the capacity multiplying the nominal voltage multiplying change in state of charge. When computing total energy for a multi-cell battery pack, we have to remember that every cell could have a different total charge capacity and could have a different present state of charge. So computing battery pack available energy is a three-step process. First, we have to determine how much charge could be removed from the battery pack before any cell encounters its minimum state of charge. Consider the drawing here. The left part of the drawing shows the present condition of the battery pack. One of the cells in this drawing is fully charged and another cell at a slightly lower state of charge. What we are doing with the first step is performing a thought experiment, not a physical experiment. And then our thought experiment, we ask how much charge could be removed from this series connected battery pack before any of these cell is discharged to the level Z minimum. And that's the state that's shown on the right side of the drawing. To compute the amount of charge we can remove, we being with a generic state of charge equation that we saw in the previous lesson. That says that state of charge is now equal to the some initial state of charge minus the quantity of ampere hours discharged and then divided by the total charge capacity. Next, in our thought experiment, we substitute the present state of charge for the initial state of charge because that's where the battery pack on the left side of the drawing is beginning. And then we set the final state of discharge to be the minimum state of charge, and then we set the capacity equal to the capacity of this cell under consideration. This is in order to figure out how many ampere hours of the charge can I remove from each cell starting at its present state of charge to see how many it takes to get down to the minimum state of charge. We rearrange the expression to find that the ampere hours discharge are equal to the capacity multiplying the present state of charge minus the minimum state of charge for any of the cells. So the maximum amount of charge that could be withdrawn from the battery pack before the weakest of the cell is discharged to Zmin is the minimum of all these, which is given by this equation here. The equation tells us the maximum number of ampere hours that can be discharged before any cells encounters the minimum SOC limit. So that's how charge is possible to remove from the battery pack. But if we were to remove this many ampere hours from the battery pack, only one cell would end up at the state of charge Z minimum. All of the other cells would end up at slightly higher state of charge. So to compute the amount of energy removed, each individual battery cell, we have to use the energy relationship from its own starting state of charge to its own ending state of charge using this accumulated number of ampere hours removed. And the ending state of charge is equal to the beginning state of charge minus the quantity of charge removed divided by the total capacity of that cell. So we are going to call that Z low, the low state of charge after this thought experiment after removing as charge as we can from the battery pack, where Z low is going to be the Z minimum for one cell, but it is going to be a somewhat above Z minimum for the other cells. So now we can compute the amount of energy removed for each cell and the amount of energy for the battery pack. The amount of energy removed from the battery pack is the sum of all the energies removed from the cells, and this equation shows the computation. You can see that the battery pack is the summation over all of the cells in the battery pack of the quantity where we multiply the capacity of that cell by the integrated open circuit voltage relationship, where we integrate between the present state of charge and the low state of charge for that cell. Now remember, it's not possible to extract all of this energy at high rates in cold temperatures because of the resistance of the cell, and that's why we needed the power estimate as well to tell us how quickly we can extract this energy. When we compute the energy estimate, there is an integral equation involved that might look somewhat frightening. But this integral relationship can be pre-computed offline and stored in a lookup table for essentially instant computation in a real-time environment. Here you can see a block of code that's written in the programming environment for MATLAB or for Octave. And this code has two sections. One section performs this integral approximation and stores it in a lookup table, and the second part of the code looks up a value from that table whenever we require it. In this code block, everything that has a % symbol at the beginning of a line that's shaded in green is a comment to describe what's happening. It's not a functional line of code. It's there instead for the human being reading the code to understand better what the code is intended to do. So if we look at this, we see that in reality there are actually only two lines of code in what I am showing you, and the rest is the description of what those two lines are doing. In the code, we are first assuming that a variable called Z reference exists in our workspace, and that vector of state of charge points at which we want to compute values for the lookup table. That's it. So, as an example, this vector might contain points between some minimum state of charge and 100% state of charge in increments of 1% state of charge. The variable OCV is a vector of open circuit voltage values that have been computed somewhere else for this cell that we are considering and correspond one-to-one with the state of charge points in Z reference as the open circuit voltage values at those state of charge. And based on those values, we would like to integrate the open circuit voltage relationship versus state of charge for that particular range of state of charge points. The code that performs that operation uses a command called CumTrapZ, which performs the trapezoidal integration cumulatively over the points of OCV wake as related to the points in reference Z. The figure shows the results of this computation for the 6 different cells you saw earlier, where their OCV, that is open circuit voltage relationships, were plotted for you at that point. In this graph, the two lines at the bottom correspond to the 2 iron phosphate cells that has slightly lower open circuit voltage than the other 4 cells. The other 4 lines that are nearly on top of each other in this integrated relationship are for the other 4 cells of lithium manganese oxide and lithium cobalt oxide, and nickel manganese cobalt oxide. The integrated open circuit voltage relationships are nearly about not quite linear. So we see that the approximation to the integral of nominal voltage multiplying a change in state of charge would not always be very inaccurate. Sometimes it's a pretty good approximation, but if you were to hold a straight edge up, you would notice that there is some curvature, especially in the top 4, and for best accuracy you would perform the computation that now you see how to do using the code. So the first line using CumTraps forms the integrated relationship, and if we want to use this integrated relationship in a lookup table, we use the next line of the code. We want to perform a table lookup into the table that has one column in Z reference. Those are the state of charge points at which the table exists, and the other is the integrated values that we called IV Z reference. In MATLAB and in Octave, table lookup is performed by the interpret1 function, which performs simple linear interpolation, and this command produces integrated voltage as a function of state of charge, or what I am calling in the code IVZ, using interpolation with this table defined by Z reference on the horizontal axis and IVZ reference on the vertical axis. Since Z reference does not go below Z minimum, we have to be very careful not to try interpolating into this table using arguments that are less than Z minimum, which is why you can see in the input to the interpret1 command I have maximum, Z minimum and Z to make sure that the input argument is never actually below Z minimum. You could also do something similar to make sure that the argument was never greater than 1 by using a minimum of Z maximum and Z, or a minimum 1. Z in there to enforce that it was always less than 1. So overall, I hope that now you have seen this code, you agree that computing this integrated open circuit voltage is not specially difficult, and that using it is also not especially difficult in an application.
To summarize what you've learned in this lesson, you can now compute estimates of battery pack power over some future time horizon, and you can also compute estimates of battery pack energy by expanding on the methods that you learned last lesson for single cells. You've also seen the first example written in MATLAB code, or Octave code, that is able to implement the lookup table, and while we applied it to the example of computing energy, the basic principle of computing and implementing a lookup table is quite general, and we will find it to be very useful throughout the specialization. This lesson has brought you to the end of our discussion of requirement 3, placed on battery management systems of performance management. We'll spend much more time examining other methods to estimate state of charge in available power in the battery pack in courses 3 through 5 of the specialization, and the methods that you learned turned out to be better than what you've learned so far. But the methods that you have learned so far give you a good basis for understanding the general ideas involved, and are sometimes used in practice even now. So, the remainder of this week will be devoted to considering the battery management system requirement, which has to do with diagnostics.
So far in this course, you have learned about the battery management system requirements 1 through 4. In this section, you will learn about the final requirement number 5, which has to do with the diagnostics. Diagnostics involve abuse detection, state of health estimation, and state of life estimation. In many and maybe even most applications, the battery management system is not in control of its own destiny. That is, the battery management system provides advice or guidance to the host application regarding what are the maximum power limits of the battery pack and how much energy is available and so forth. But the host application might choose to ignore those limits or might fail in some way that causes those limits to be violated. The battery management system must detect and log external abuse conditions. These might include a violation of voltage limits or a violation of current limits or violation of power limits or of temperature limits. Any of these abuse conditions would result in severe damage to the battery cells and to safety concerns. The photograph here shows a mobile phone battery that has been overcharged. In this case, that has caused the electrolyte to break down and to form gases which then cause the cell to expand in volume. These gases sometimes include hydrogen gas which is flammable, and so if the cell is punctured, it could cause a fire hazard. All of these abuse conditions that are detected, whether they happen to be, must be logged as we talked about under requirement 3 for warranty and post-mortem diagnostics. In addition to external abuse, the battery management system must be able to detect and to log failures of its own algorithms and components. This includes detecting failures in the sensor that measure voltage and current and temperature. It includes being able to detect a failure in the balancing or the equalization system of the battery pack. It must be able to detect failures in the contactors of the thermal management system. It must be able to detect loss of communications with the host controller or frequent and repeated traveler or missed message with the host controller. The photograph here shows some failed components on the circuit board of a random electronic device that were caused by the bad capacitor design. These capacitors have become swollen and the electrolyte has leaked out of the cases, causing the capacitor to fail. The failure of an electronic component like this could cause any of the internal failures I mentioned earlier. And it's important to be able to detect these failures so that they can be communicated to the external host and to diagnostics so the battery pack can be repaired and used safely. The battery management system must be able to compute and report an estimate of the state of health of the cells of the battery pack. Earlier, we saw that state of charge of a battery cell is tied very directly to physical quantities inside this cell, particularly to the average concentration of lithium in the electrode. State of health is not defined quite so precisely. State of health is generally trying to quantify how much a cell has aged to this point in its life. And so, we could say that a state of health indicates a brand new healthy cell, and a state of health of 0% indicates a cell that has reached its end of life. There are two measurable indicators that are frequently used when people talk about state of health, and over cell lifetime, one of these is capacity, which starts at 100% and decreases by about 20 or sometimes 30% before we consider that cell have reached its end of life. Now, still cell has 70% of its capacity remaining, so the cell might be still very useful in a secondary application, but it's not considered to be useful any longer in its primary application. Similarly, the resistance of a battery cell starts at some value and might increase 50% to 100% over the lifetime of the battery cell. We refer to the first measure of aging as capacity fade because we are losing capacity over time. We refer to the second method of aging as power fade because When resistance increases, the ability to extract power from the cell decreases. So when we learn how to estimate cell resistance as it changes over time, and how we estimate the total capacity of a cell as it changes over time, we will be able to provide a state of health measure to the host application. And that's the next topic of study in the specialization. It's also possible to define a state of life indicator, which tries to predict how much life remains as a percentage or as an absolute value in terms of calendar time. Notice the fundamental difference though between state of health and state of life. State of health is an estimate, whereas state of life is a prediction. State of health uses all past and present data to estimate a current condition of the cell. State of life attempts to predict instead what will happen in the future with that cell, and we don't have the luxury of knowing how that cell will be used in the future. So the issue is that the future rate of cell abuse and cell aging may differ from how the cell has been used in the past. So state of life prediction tend to be quite inaccurate at best. So at this point, you have been introduced to the 5 basic battery management system requirements, and one that you learned about in this section has to do with diagnostics. You have seen that a battery management system must be able to detect and to log external failures that impact the battery. The BMS must also be able to detect and to log internal failures that impact the battery. Also, the BMS must be able to monitor normal degradation as reflected by a state of health metric, and in some applications, we may also wish to predict a state of life metric. This brings us to the end of our discussion of BMS requirements.